but then you start doubting that observation. So when a spin up was measured, you say we have to be critical then. Was that really a measurement?
Exactly. Even performed measurements have no absolute outcome.
Vienna, Austria. This is where I met 3 award-winning quantum physicists who are basically proposing a new approach to physics. Here you see me and cameraman Max, and we're in a room filled with some of the smartest quantum physicists on our planet. They're talking about stuff we didn't understand. But in this video, I'm going to try and share with you what happened in this room and why I consider it to be a silent revolution in the foundations of physics. Now, this video consists of 3 parts. In the first part, I give you a 15-minute overview. In the second part, I have a long conversation with physicists Eric Cavalcanti, Renato Renner and Caslav Brukner. And thirdly, for those of you who want to understand the math of it all, I included 3 full conference lectures given by these 3 physicists. Now, please like and subscribe. It really helps us making content like this. And let's dive in.
These theorems provide new challenges for the interpretation of quantum theory, forcing us to make some hard choices in our conception of quantum reality.
Meet physicists Caslav Brukner, Eric Cavalcanti and Renato Renner. In their award-winning papers, they describe quantum scenarios that make the theory much more crazy than it already is. The way they do so is by including observers like Alice and Bob, Charlie and Debbie into their quantum models. But first, let's take a step back to when Alice and Bob still were only just on trains and stations.
You're measuring a longer time than Bob is. So from your perspective on the platform, time has slowed down for Bob. That's time dilation.
Since relativity theory, we know that Alice and Bob can experience weirdly different things depending on their reference frame. For instance, Alice can see 2 lightning strikes simultaneously, whereas for Bob, those exact same lightning strikes happen with time in between. Now back to you watching this video. You have a way to make sense of these seemingly contradictory experiences of Alice and Bob by applying physics, relativity theory in this case. And this brings me back to the title of this video. Physics as we know it gives us this objective viewpoint.
At least in general relativity, we can say that in certain patches, if the coordinate systems overlap, we know how to transition from one to the other. That one has a manifold of space-time that one could in principle look at from the outside. Of course, no one has this outside view, but we can just construct it as an object, which somehow reflects the fact that there is still some, let's say, intersubjective agreement between the agents.
Reality as this intersubjective agreement. Think of it as a theater show in which we all have our individual experiences depending on where we sit in the theater. We sometimes might argue over what we've seen, but in the end there always is a script that perfectly describes what has actually happened on stage. Now, Cavalcanti, Renner and Brukner have come up with events that cannot be scripted.
Because now we're finding that the events themselves are relative. And so no longer there will be a way to transform from one quantum reference frame, if you want to put it that way, and back again.
We have at least not found a way to find this like common perspective.
No common perspective. What are we talking about? You probably have heard of Schrödinger's cat and it being dead and alive at the same time. Now, I always thought that the moment the observer opens the box and finds the cat hopefully alive, it then is alive to all observers outside the box. But back in the 60s, Eugene Wigner made clear that the cut between our quantum and classical world is not so clear. Wigner thought the following: what if I have a friend in a lab with a quantum system and I'm outside that lab and perfectly isolated from it? So to me, the friend and that quantum system are both in a superposition. Now, if we translate this back to the Schrödinger's cat scenario, this could lead to the paradoxical situation where Alice in the lab has measured and seen the cat either dead or alive, but to Bob outside the lab, Alice is still in a superposition of having seen the cat dead and alive. Now, the difficulty with Wigner's friend is that you can always draw another Wigner box, another quantum box around an observer. Get this observer observing an observer observing an observer observing an observer. This can go on forever. So back to the theater metaphor, it would mean that where the stage ends and the seats start, or who is an actor and who is part of the audience, is undecided. You might think you are observing a show and it has ended, for instance, but to someone else, you are part of it and it's still open-ended.
And what is really crazy for me in the whole picture is that during this experiment, I can receive some information from the other bubble. For example, a friend can say, look, I really have a definite outcome. I performed the experiment and I have a definite outcome. I cannot tell you which one, because then it will collapse the whole state and we will not finish the experiment. But I promise you, I'm your friend, I don't want to lie you. I heard a definite outcome. But when he does this and assign now which outcome has been observed in friend's experiment, together with the outcome that he observed in his, then he runs into the Bell's type problems.
Basically, what Caslav is saying is that there is no outside way to describe the whole picture in these Wigner friend scenarios. Basically, we've lost objectivity here. It made me think of these Asher paintings where for a certain observer things feel completely logic, but when you zoom out you just see contradictions and paradoxes all over the place. Now, should we really worry? Not yet. The experiments these physicists propose are very hard to put to the test. But looking back at the history of physics, we should be on our guard when strange thought experiments are proposed.
At the time of Bell, after Bell's theorem in the 60s, it starts strongly and it still goes up. And now the paper is by far the most often quoted paper by Einstein, and is quoted nearly twice a day.
This is Nobel Prize winner Anton Zeilinger, and he's talking about a paper from 1935. The authors were Einstein, Podolsky and Rosen, and in the paper they described a crazy but hypothetical implication of quantum mechanics that no one at that time really worried about. But around 40 years later, that phenomena would turn out not to be hypothetical at all. It is called quantum entanglement and it is absolutely real. We just met each other. I'm just saying on camera for our audience. So we just met you, and you're a master student of Anton Zeilinger.
Yes, exactly.
And you were explaining to us that this is really cool, right? So we are standing right here, right now.
Exactly.
And what do you guys do? What's this beam?
We shoot entangled photons over a 10-kilometer free space link. So really just over buildings, people's cars. This is our
there it is.
Our telescope, and we're going up all the way.
Telescopes like these are used to perform Bell tests, in which pairs of entangled photons are separated over large distances to then perform measurements on them. Now, Einstein understood that these particles with large distances in between would show very strong correlations, spooky action at a distance. But the way to account for that, he thought, would be so-called local hidden variables. The way I think of it is some sort of agreement of those particles in their paths that accounts for the fact that when you measure a spin up, the other one will always measure a spin down. Like this agreement they made. And this agreement plays out to us as a form of magic, that spooky action at a distance, but in the end it's just a smart algorithm they play out. A way to understand this that I find funny is that these photons are like suspects.
Where were you last night?
I told you a dozen times I was at the movies.
Then, explain this to me.
If you would suspect Alice and Bob are partners in crime, as a good cop, you would do anything to establish their conspiracy, to find these local hidden variables.
Why don't you come clean? Make it easy on yourself. Tell us the truth.
Well, I ain't talking. You got nothing to book me on.
John Stuart Bell was like this super detective who found the ultimate protocol to expose the most clever conspiracies. And lo and behold, in all Bell tests, local hidden variables are ruled out, at least so far.
Frank.
I'm afraid he's right. We're going to have to let him go.
And physicists have really gone to great lengths in these tests. For instance, Anton Zeilinger, who used in a so-called cosmic bell test light from 7 billion years old quasars to guarantee pure randomness, which you need in these tests.
So we took quasars out by billions of years and took the random numbers, randomness in their light to trigger.
Okay, why did I start telling you about John Stuart Bell? Because his work is a clear example that we do need to worry about seemingly abstract and innocent thought experiments, no-go theorems, as physicists like to call them. Because what Bell did was that in a certain sense he debunked two metaphysical assumptions. Locality, in the sense that particles are only influenced by forces in their direct environment, and realism, in a classical sense that particles are predetermined. But before you misunderstand this, Bell did not prove that nature isn't local or isn't deterministic. He just proved that it cannot be both at the same time. And that's what's called a no-go theorem. Einstein said that he liked to think the moon is there even if we don't look. He saw himself as a realist and he wanted an observer-independent universe. But Bell's theorem and the Bell tests make clear that Einstein's metaphysics of an observer-independent universe is in deep trouble. And the irony to me is that Einstein, by writing the EPR paper, paved the way for this metaphysical crisis. I think in Freudian psychoanalysis you have this concept of the flight forward into your fear, leaning into your fear. Did Einstein just wanted to look his fear in the eyes and get it over with? It's almost as if Einstein foresaw that the real bomb of quantum mechanics was not the nuclear one, but a metaphysical one.
Metaphysical assumptions that ordinarily you would take to be metaphysical in the sense they are referring about ontology, epistemology, about what exists and how we can know about it, making those kinds of distinctions that typically are not made in physics, that they can be put to test. That there are some experiments you can do that can rule out certain conjunctions of metaphysical hypotheses.
If you think about this cup, you can describe this cup in terms of some properties. It's white, it has this form. You can surely think that these properties are there even if I don't look at them. And Bell's theorem challenged this. One possible reading of that is that if you observe the color of this cup, you should not think that the shape exists.
But then one alternative to resolve Bell's theorem could be just to say that event that you observed is somehow created at the time that the measurement is done. And prior to that, it doesn't have an existence.
Unperformed measurements do not have results. So you basically say, I'm okay with the fact that physicality only presents itself upon measurement. Weird as that may sound, that is the way in which many physicists come at peace with the weirdness of Bell's theorem. But these three physicists combine Bell with Wigner's friend and create these extended thought experiments, and then things really get crazy because now you also have to start doubting performed measurements and their outcomes. Saying something like unperformed measurements do not have results, but performed measurements may also not have results.
But then this way out of resolving the theorem by just saying unperformed measurements have no results doesn't work. Because you have to say that this measurement, this observation for this observer inside the box has no results.
Now, Cavalcanti, Renner and Brukner were awarded for their work because they arrive at these insights formally through no-go theorems that build on Wigner and Bell and combine them in crazy ways, and that, like Bell's theorem, can potentially be tested.
I like to call this field, not me, I'm using Shimone's term, experimental metaphysics.
Once, physics gave us an objective shared world for free. and it had subjective experience as its hard problem. Could it be that a future subjective physics has it exactly the other way around? That if you take subjective experience as more fundamental, you now have the challenge of getting to an objective shared world?
I will hit this desk and you hear this. And we can maybe agree that this is an event, that this is something which really happens. There is some uncomfortable situation that in everyday life we are used to learn from other people what they have done and combine this knowledge with our knowledge. These no-go theorems suggest that we should not do that, or there is no compatible way to do that.
And this is just crazy stuff for
it's
people
crazy
to understand.
for us as well.
Yes. I mean, it's not really acceptable, but it's... I have this perception, that's at the very start, that's the most certain thing in the world, is that I feel this. It's much more certain than that atoms somewhere out there exist. So for me, this is a starting point. And now maybe we develop this desire to kind of find a common picture, which seems fragmented. But maybe I should just start from there and say, there are these perceptions that I have, and that's how we should start with physics. So it puts me in the center.
Welcome to the Essentia Foundation's YouTube channel. We are here in Vienna covering the Quantum Foundations conference hosted by ICOKI Institute, celebrating 20 years of ICOKI and 6 years of Bell's theorem. And at my table, I have 3 quantum physicists who are all 3 winners of the Paul Ehrenfest Best Paper Award for Quantum Foundations. It's an honor to have all 3 of you here at one table. And we thought, to who can we talk better than to you 3 about what's happening at the cutting edge of quantum foundations, as your work has been now sort of honored with this award. So very welcome, Caslav Brukner, Renato Renner, and Cavalcanti. Great that you guys are here. And in this conversation, we'll touch on each of your papers. And maybe as a first question to get our audience there, many people watching are quite familiar with the strangeness coming from Einsteinian relativity, time dilation, distortions of space-time. And we have movies about that, like Interstellar, and so we are sort of getting used to that. And many people are not used to the quantum strangeness yet, which is, of course, your work. So maybe as a first question, on what particular quantum phenomenon, quantum weirdness, does your paper focus and is sort of your line of work? So maybe nice to start with you, Caslav.
Thank you for inviting us here for this interview. I guess I may share this enthusiasm with others that possibly the largest surprise that we face in quantum mechanics is related to 2 puzzling Gedanken or real experiments. And one is that Bell's theorem, and the other is Wigner's Gedanken experiment. And I can shortly introduce both of them. Bell's theorem tells us that we cannot assume, in one reading of that objects possess their properties prior to and independent of our observations. So if you think about this cup, you can describe this cup in terms of some properties. It's white, it has this form, and you can surely think that these properties are there even if I don't look at them. And Bell's theorem challenged this. One possible reading of that is that you should not go that far and assume things that you don't directly observe. So if you observe the color of this cup, you should not think that the shape exists at the same time, or the other way around. That's one of the puzzles. The other puzzle is the Wigner's friend experiment. This is an experiment that involves 2 observers, encapsulated observers. One of them makes just the usual observation, maybe some quantum mechanical experiment, and obtains some outcome. Well, maybe this observer measures the color and finds it's white. And then there is another observer who treats the first observer and the system observed as one unique quantum mechanical object. This other, we call it Wigner, doesn't make any measurement of the color of the cup, but makes some very complicated measurements. And in this other paradox, one possible reading of this other paradox is that there are quantum mechanical descriptions of what's going on do not match.
That's really interesting. We'll go deeper into that. And for our audiences, basically Wigner's friend draws, when we have a classical double slit with an observer and a system, we now can always draw another box and set someone outside of that, right? And is it right to say, but you could always draw another box and put an observer? So that sort of leads to very interesting paradoxes and levels of complexity. And to move on to you, Renato, what puzzle, quantum paradox fascinates you in particular? Because this all leads to inconsistencies, right? And that's, I think, your work.
Right. So I can say I agree with the enthusiasm that Caslav has for these two thought experiments, or one of them is a real experiment, the other one is a thought experiment.
Yeah, Bell has been done. Yeah.
Right, Bell has been done. And Wigner's friend experiment is extremely challenging because we would have to do this complicated measurement that Caslav just mentioned on the observer. But for me, one of the, let's say, most puzzling things about quantum theory is if I look at the theory as a theory of reasoning. So if we ask ourselves, quantum theory is a way we want to make predictions, then we realize that in these thought experiments, we actually don't know how to make these predictions. And at the end, if we analyze or try to come up with a statement about Wigner's friend, we find that the formalism of quantum theory as we have it today doesn't provide an answer. At the end, there are interpretations, or so-called interpretation. It's actually more than an interpretation. I really need to understand more to be able to give answers to certain questions. I mean, a question could be, is the outcome that the friend measures who is in an isolated lab actually unique? Is there only one outcome, or are there two outcomes in two parallel worlds? And that's, of course, then linking to, for example, the parallel worlds interpretation. And you see, these interpretations partially actually came out exactly of this puzzle connected to Wigner's friend, that we didn't know how to interpret that. And there are different ways to see it. And I kind of saw this as an incentive to move these questions, which are, in a sense, or sound as philosophical questions, in the sense that one can talk about them but not do an actual experiment. I thought maybe one should actually try to come up with different types of experiments, extensions that move that into the realm of physics. Because for me, it's really a physical question, even though it sounds like an interpretation. Does there one outcome exist? Are there two? I mean, this is for me something I want to understand as a physicist. And so for me, the Wigner's friend experiment is, in that sense, one of the most important thought experiments, because it challenges this connection between the mathematical formalism of quantum theory, which we seem to understand very well. I mean, quantum theory has predictions which are incredibly accurate for the experiments we can do. And on the other hand, we see, when we look at these experiments, that we seem to understand almost nothing, because we don't even have answers to this, in a sense, conceptually still relatively simple situation. And that's, I think, one thing that I find extremely fascinating. We have such a theory which is so accurate, but nonetheless, if we extrapolate it to these setups, we have no clue what's going on. And so that's a good starting point to work. And for me, that was one of the...
That's very, very, very interesting. And what you said, that sort of we live in a time now where sort of questions previously thought of as merely philosophical or metaphysical can now somehow be put to test, be it still maybe in sort of no-go theorems and not yet experimentally, but still that's interesting. And that brings us, I guess, to your work, Eric. I mean, you are comfortable with being called an experimental metaphysicist?
Yes, I'm probably the only person in the world that calls himself that, but I mean that very seriously. Experimental metaphysics, the term, I thought it was actually coined by Shimony, but recently I learned it was coined by Michel Bessel, who was a friend of Einstein. But Shimony was referring to Bell's theorem when he was talking about experimental metaphysics, which is sort of the first time that physicists realized that metaphysical assumptions that ordinarily you would take to be metaphysical, in the sense they are referring about ontology, epistemology about what exists and how we can know about it. We're making those kinds of distinctions that typically are not made in physics, they can be put to test. There are some experiments you can do that can rule out certain conjunctions of metaphysical hypotheses or different conjunctions of hypotheses about reality and physics, right? In some sense, it's metaphysics in the sense that it's comfortable with talking about words like reality and words like ontology and epistemology. In another sense, you can think of it as metaphysics in the sense that it's the study of the landscape of physical theories, the study of physical theories themselves, whereas physics is studying the world. But ordinarily, a physicist is trying to construct a theory that will make some predictions about the world that can be put to test. And I think experimental metaphysics is looking at this from a broader level and looking what different possible ways can we construct these theories, and not just distinguishing them in terms of the predictions that they make, but also in terms of the metaphysical picture that they paint, right? The way in which they explain reality.
And it's very nice to, with all three of you, and maybe we can just organically get to your papers, right? Instead of just presenting your ideas, but if you all three feel free to just bring in your own perspective on this question. But how the metaphysics has progressed. We had, of course, Einstein thought of very often as a realist, but that term already is sort of difficult. I mean, when I talk to physicists, I mean, there's not an agreement what we really got. And then you have scientific realism, and sometimes we say naive realism, and that sort of feels comfortable to discount. But Einstein was thought of as a realist, right? He has famously quoted, "I like to think of the moon existing even if I don't watch." Okay, that was sort of his ontology. Mm-hmm. And therefore he had troubles because he saw the implications of quantum theory and where it would lead, and that gave us the EPR paper, and that led to Bell. And then for the first time, you could say that was like a metaphysical test done in this Bell inequalities. And now we have the question whether we want to give up on locality or realism. Is that it? Am I saying it correctly then?
I think I prefer to be more careful with the terms.
Yeah,
myself,
please do.
Because, for example, a term like realism is often used not very precisely, right? So I think there's more precise ways of formulating Bell's theorem, right? But once you do it, you can get to a long list of background assumptions. But sometimes the assumption of realism is really meant to mean something like what Caslav was saying before, which is the assumption that there exists some factors, some physical states, some ontic states, which predetermine the outcomes of measurements for any measurements that you can make. But then really it's an assumption, it's better to call that assumption something like determinism or predetermination, not realism as such, right? So it's it's better to be a bit more careful there. And locality also is used in many different ways. That's another problem. It's a word that many debates about the meaning of Bell's theorem end up being about different ways in people are using the same word. And locality is one of those that has this difficulty, because one way in which you can think of that, which was the way the originally Bell used in 1964, was that locality is the assumption that if you make a choice here, right, and let's assume that's a free choice, a choice which is made with some free variables that are uncorrelated with the experimental setup that the physics of the setup that you are studying. That choice can have effects in its future like coin, right, but not at a distance instantaneously. But also it's possible to make to derive Bell's theorem with an assumption which later Bell called local causality, which is a little bit more subtle, which you can think of as going back to a principle that's called Reichenbach's principle of common cause from Hans Reichenbach. He was a philosopher that studied philosophy of time and causation. And it's the assumption that if there's a correlation between events, right? You see, There's a story that Bell used that we heard in the beginning of the conference, which was about Butterman's socks. Bell's friend and colleague, Butterman, he always used socks of different colors. One is pink and the other one was some other color. And then knowing that about his friend, if you see one of the socks and you see that it's pink, then you can predict that the other one is not pink, right? And there, because there's a common cause, the common cause being the fact that in the morning, Butterman woke up and being Butterman, he decided to put a pink sock in one leg and another sock that's not pink in the other leg. So there's a common cause. The correlation between these separate events can be explained by the fact that there's a common cause. But then given the information about that common cause, the events are separately explained, right? It becomes irrelevant about, the other event becomes irrelevant for predictions about this one here. And that's a stronger assumption than the assumption of locality alone. So there's different ways in which you can derive the theorem.
Yeah, and for both of you, Caslav and Renato, if we want to be precise, and for instance, the term realism is of course difficult then. But reflect on that, would say has something to do with observer-independent physical properties. So a particle unobserved in a state has a spin up, whatever already, and the moment I measure it, I get to see it. And it might be in a superposition of both, but it has those physical properties. That's my understanding of what I would say that's a realist approach, right? Is that a good definition? And
I think this is quite a good definition. I think we can also relax this, as Eric said. One possible relaxation of that is that you don't say that a particle carries a definite properties along all possible, for all possible measurements, actual but also potential one. You can also think about just if there is a joint probability for all possible outcomes we could imagine, of which only subset we will actually perform in experiment, and most of them will not. And this is also related somewhat to counterfactual reasoning. You know, you assign some entity, which is a joint probability for all these possible measurements. And to take your example, I measure spin along z direction, but at the same time, I assume that there is a joint probability for both z and x. And for some reason, quantum mechanics has this epistemic restriction. It doesn't allow us to look at the same time z and x. So you can just choose one or another. And that was a dilemma also historically in quantum mechanics when Heisenberg came up with the Heisenberg uncertainty relation and not being able to observe at the same time position momentum. But this doesn't prevent you to go further and to think like, oh, even if I have this epistemic restriction, the nature is not like that. There is, at least probabilistically, I can assign these joint probabilities for all possible outcomes. And then one possible reading of Bell's theorem, and I'm all very personal because I keep some kind of notion of locality, is that this assumption is wrong. And that, as Asher Perez would say, unperformed experiments have no outcomes. And I somehow found a peace with this and say maybe simply these small systems have not enough information content to store all possible answers to all our experimental questions. Maybe just for that one that you pose, but not for all others. And this gives some insight why it could be possible. Now, that's not the end of theory, because what we now looked in our different variants of this extending Wigner's friend scenario was, okay, don't talk about these counterfactual things. Let's talk only about what you observe. And then we are not committed to this strong realistic attitude of thinking about something is real even if not observed. However, all these different theorems combined observation of different observers. Then you can still think, can we assign reality to these observed events of different observers?
Yeah, are there then shared facts in the worlds because they have those measurements have been performed, they have outcomes, those are now facts, we can talk about those, and then we have a reality again. A shared reality, yeah.
We should have a shared reality. But what our theorems indicate, that this have, again, the same price as Bell's theorem. And one possible reading of that, if you want to consistently read in the same way as I read Bell's theorem, there is no shared reality.
That's crazy.
I would agree with that, but if I may add something,
yeah, please
because
do.
You mentioned the Bell experiments that have been conducted, which is of course true. But what Caslav just pointed out, this fact that even though we have this observation, there is no reality, means that it's not clear that these experiments actually did what would supposed to be done, because what you want to do in a Bell experiment is to do a measurements at two space-like separated locations, which means actually at a particular time somewhere. So I'm somewhere in Alice's lab that is remote to Bob's lab, and Alice will measure something, and what you need is that this measurement outcome actually becomes a classical outcome, whatever that means, but it means somehow this outcome now exists. And that's an assumption you need to make when you want to analyze these experiments. So all the experiments that were done, including the so-called loophole-free ones, still have the assumption that once the measurement was performed, now I could ask, what does this mean? But once the outcome of the measurement was probably in the computer that would register the outcome, then we declare this outcome to exist, in a sense. And you need that very well-defined point in time to then verify that you actually satisfied the space-like separation of the two. So you have to impose an assumption that from a certain time on, an outcome exists, or is there, or is... One could use different terminology, but at the end what is important is that this point in time defines whether you satisfied the space-like separation.
But it's from an outside perspective, from a non-physicist perspective, it sounds like crazy, because you start to doubt the very thing that I thought we were agreed upon when we before measured C and outcome. Okay, that's that. But then you start doubting that observation. So when a spin-up was measured, you say we have to be critical then. Was that really a measurement?
Exactly. I mean, that's what I think Caslav said. And I said, this actually has an experimental, it has an impact on how we should do experiments. You know, if I do a measurement, at the end, I will, as an observer, usually know the outcome. So I observe it and I see now this cup is here. So I've performed the measurement. Now in a Bell experiment, we cannot go that far usually, because we have to do the measurement extremely fast. The experiment has to be completed before a beam of light could have traveled from Alice to Bob. So from the point on when you start the experiment, and for the start, by the way, you have a similar question, when does it mean to start it? It's actually when you make the choice what to measure. Until the point you have the measurement result, very little time can pass. So if you
just side note, Renato, where are we now? How much sort of the Bell test? How much kilometer in between?
Yeah, I mean, let's say if you do a Bell test, I mean, I could give an example. At ETH and my university was recently a new loophole-free Bell test carried out. Alice and Bob are separated by 30 meters. Now this means the time you have to carry out the measurement is just the time that corresponds to light traveling 30 meters, which is a very small fraction of a second. It's certainly smaller than any human being could realize that the measurement was, or to actually see the outcome. So if we wanted to go to a kind of careful definition, which is still potentially problematic in view of what Caslav said, we could say once an observer has registered the outcome, and I've seen this cup is there, I can say now it's really there. So even that is doubtful. But now in a Bell experiment, the experiments that were carried out, we had to do it much faster. So there was just somehow at the point when the result was registered by the computer, we would say the measurement is now concluded in order to be sufficiently fast. So we had to impose kind of constraints. Someone could say there are now two options. Either we repeat the Bell experiments and do it on a much longer distance, for example, between the Earth and the Moon. There we have 1 second of time. This is probably enough for a human to actually see the outcome and realize what the outcome is. And then one could say if maybe, I mean, in principle, it could be that then the Bell experiment fails. There's no longer a Bell violation. It's not what I expect, but in principle, that could happen if it was really something like the human consciousness that would have an influence on that. That's not what I believe. I think it will still give the same result. And the other thing that could indeed happen is that we still get the usual Bell violation, but that then still is in conflict now, as we have shown with these experiments that we proposed. We will still get contradictions if we now look at it from the perspective of these extended Wigner's friend experiments, which also involve, again, the Bell experiment in some way. And so the conclusion in that case would be, not even when I saw this cup, it's actually a fact that everyone would agree with. So that's the other conclusion that could happen. So either the Bell violation will stop to appear, in which case we kind of can save our old picture potentially, that there are facts, at least once we have a conscious perception of them, or, which is for me the much more likely option, the Bell violation will remain even for these, let's say, astronomical experiments. And in that case, I see no other choice than somehow giving up our common understanding, or let's say the common sense understanding of what are facts.
Very, very, very interesting and troubling. And we've hit earlier than I thought in this conversation on consciousness, because that's what you're saying, right? We haven't yet performed Bell tests with conscious observers because we simply cannot, but in practice, or in theory we can, so that moon example. Eric, if you had to reflect on what Renato just said and also sort of relating that to consciousness, what are your thoughts and how does that relate to your work?
So, I want to do that at the same time, and maybe putting a little bit more context in how the experiments that we are proposing differ from Bell experiments, right? Or the assumptions in particular. So what Renato is saying, essentially, it's what I call absoluteness of observed events, that when an event is observed, it becomes, it's absolute in the sense that it's part of a shared reality, right? There's a truth to a proposition that's saying, I have observed this cup, and that truth is universal and absolute and not just relative to me, say, or to a branch of the wave function or something like that. So that's one assumption. And that assumption is also necessary in the Bell experiment, which hasn't always been made very explicit, but there is an assumption, as Renato is saying, that we assign some absoluteness to that event. We assign a fact, an event having occurred at a certain point in space-time. That's an important assumption. The other assumption was locality. So I'll use the sense of locality in which if I make some free choice here, I cannot that cannot influence events which are outside the future light coin, right? Which I cannot reach with a signal traveling at speed less than light. But in a Bell experiment, there's also the assumption of predetermination, which is what often people call realism, right? That there's the outcomes of these experiments, and they are predetermined. They are determined before you perform your measurement, independent of what measurement you will perform.
Local hidden variables.
There's some local hidden variables.
Yeah.
But then one alternative to resolve Bell's theorem could be just to say that event that you observed is somehow created at the time that the measurement is done. And prior to that, it doesn't have an existence, right? Alternatively, you would say also that Reichenbach's principle of common cause fails in quantum mechanics. But you can say that and somehow maintain a notion of some absolute reality. It's just that at some quantum level, reality is a little bit murky.
Yeah,
but
so
at the ordinary
to
level,
grasp what you're
still
saying, so when it's produced upon measurement, it has no properties before that can still give us a fundamental nature of reality, but that is just a quantum
it's just
field.
That below the quantum level, before you perform a measurement, you can't talk about the outcomes of this measurement.
Yeah.
Unperformed measurements have no outcomes. It's a motor. But after the observation is done, now it has an absolute fact corresponding to it. But the problem with these no-go theorems is that you don't need to assume that. You don't need to assume that there is a fact that is determining the measurement. You only need to assume absoluteness of observed events, because now there is an observer that performs an observation inside some isolated box, right? The experiment is very hard to be done with a human being, but we can imagine, at least for now, in a thought experiment, maybe one day we can do with artificial intelligence in a very large quantum computer. We can envisage some experiment like that being performed. But now you are assigning a reality to an observation that has been performed, not to some hidden variables that are not being observed by anyone, right? And apart from that, we're assuming that notion of locality and the assumption that you can freely choose these settings, right? But then this way out of resolving the theorem by just saying unperformed measurements have no results doesn't work. Because you have to say that this measurement, this observation for this observer inside the box has no results.
I mean, just these immediate experiences, if you want. These are the events that we are taking into account, and that's the notion of reality, which is so weak that almost everybody independent of interpretation would say, okay, that's an event. Maybe it's a very composite event in some theories with the underlying structure. Maybe it's elementary, if I'm more like Bayesian approach. But we will all agree that this is an event. I mean, it pains. Yeah.
I mean, well, maybe go back to the slogan, unperformed measurements have no outcomes, and say what we did, we lifted this to say that even performed measurements have no absolute outcome.
Yeah.
So that's kind of the
You
strength.
also, and this is just crazy stuff. For
it's
people
crazy
to
for us as well.
Yes. I mean, it's not really acceptable, but
it's not
for me.
It's okay. Caslav, you just hit the table and you say that's not an event, or it's not a fact. It's not an absolute fact.
No, I said that's the fact, or fact on which we'll agree that it's a fact.
Yeah.
Yeah. We all in the room heard that, and we say, okay, that's a fact. That's the beginning of the theorems.
Yeah, okay.
That's the beginning.
That's the metaphysical hypothesis.
That's the hypothesis.
Metaphysical hypothesis.
And I think it should not be controversial, because this is how we move in everyday life.
Yeah.
But the thing is that if you assume that there are these things happening in Franz's laboratory, and also the same similar type of things like that in a Wigner's laboratory, and you think that they coexist, that you can, in terms that I introduced before, assign a joint probability both for the results of Wigner and for the Franz, then you run into Bell-type difficulties. And then again, way out is maybe to think that things are non-local or whatever. But I'm closer to think that you should not take them as the truth values that coexist. And then we are coming to the very interesting notion of maybe reality or intersubjectivity, which is divided. I can think about my events. The Wigner can say, I believe in my things. Like there is also my colleague here, and we all heard that. But I should not say anything about Franz. I should not take any statement, assign any statement with definite statement without events in the Franz lab or box or bubble, the Eric's find of world bubble. But this is the other way around. The Franz argues in the same way. So it's some kind of a, if you want, democracy about incompatible realities or intersubjectivity. Within each bubble, things look just like here, but we should not combine them. And what is really crazy for me in the whole picture is that during this experiment, I can receive some information from the other bubble. For example, Franz can say, look, I really have a definite outcome. I performed an experiment and I have a definite outcome. I cannot tell you which one, because then it will collapse the whole state and we will not finish the experiment. But I promise you, I'm your friend, I don't want to lie you. I heard a definite outcome. And then Wigner, from outside, see his definite outcome and say, I should have, I mean, I trust.
He sees the message saying that.
It's the message. The message is there is a message that Franz sends out to Wigner, and in the message says, It's written, I see a definite outcome.
It's definite, yeah.
Yeah, without revealing which one. That's important. And then the Wigner has this message and has his own outcome and says, okay, there are all reasons to believe, because I have some evidence that there is some event over there. But when he does this and assign now which outcome has been observed in Friend's experiment, together with the outcome that he observed in his, then he runs into the Bell's type problems.
And he sees a different reality, or has a different...
But
yeah, Renato, please, can you...
There's different ways out there, right? And it's also important to mention that a convincing experiment of that kind hasn't been performed. We have done a proof of principle experiment where the observer is just, let's put it that way, one particle, right? In one of the experiments that we did, it was not exactly a particle, it was a path that a particle takes. So the path becomes correlated with a property of the particle, the polarization. And so in some sense, the path is measuring the polarization because it becomes correlated with it. But that's a very simple friend, right? And most people would say that that's not an observer, right? It just confirms the predictions of quantum mechanics in principle for this very, very simple type of observer. But there's still an open question whether if you scale that up with systems that are more plausible observers, whether we will remain seeing the violations. One of the possibilities is that we won't.
Yeah, I think this is an important point to realize that the experiments confirming what we are all saying haven't been done yet. But I think I don't know, I cannot speak for the others, but many of, let's say, the younger colleagues I have at our institute, for example, would say, yeah, it's pretty clear this will still behave like that if we scale it up. Some older colleagues would be against that. I mean, if you compare this, for example, to special relativity, where we had to learn that the perception of time is not absolute, we made a similar step. And that step was also, in a sense, quite far-reaching. I mean, everyone had the perception there's time. We agree what time is. We can look at the clock on the wall and see it, and we have all a perception of time. And then somehow the lesson from general relativity is that things we thought are absolute are not as absolute as they appear to be. And maybe we are just learning that lesson again on a different level, because, of course, when Caslav hits the table, we all see it and we agree. Now, we usually are not in a situation that this room is perfectly isolated and there is some other guy outside who would then disagree with that event. So this is just not what happens in our daily life, in a similar way as we didn't usually move at velocities close to the speed of light and see the time dilation. So maybe we have this preconception because it was the simplest model to explain what's going on in our daily life. And it's a very good model. It works in all practical situations. And this is, I think, the dangerous thing in physics, that we grow up with a certain idea that things that we usually agree on are now absolute. And I think, for me, the lesson is really we should give up that idea. And that actually brings me also to the point that Lydia mentioned about what is the timing of the experiments. Because if I now try to take this seriously, and I think one always, again, falls into the trap of not taking it fully seriously. One has to say everything is now a priori just relative to me as an observer. Now also the definition of what it means to start an experiment, when do I make a choice or when do I perceive an outcome, is just now relative to me. And this, at least in this particular case, resolves for me the question, because then I could say there is no definition of an experiment has ended before I see the outcome. And now one could ask, why me? But I could say, at the end, everything is anyway only defined with respect to me a priori. Then I could, of course, try to see maybe we agree with others, but a priori, it's just subjective. So for me, it's just a lesson one has to learn again and again. And I somehow had the impression for myself, I learned it many times and never took it seriously enough. And then I get reminded I should really take it seriously.
Yeah, and that also has to do because physicists talk about for all practical purposes, right? But then for all practical purposes becomes a sort of a mindset, and you forget that it once was for all practical purposes, but at a fundamental level. And I mean, we got used to sort of the curvature of space-time, the famous sort of, if I have a fold sort of this table and then roll a ball and then we get used, that's what gravity, how it all works, because we got that image, right? And we could, in a sense, still live with it because it feels like I'm just bending reality as it is, and I can get used to sort of different perspectives. Oh, time gets longer and stretched, but I can still see how I can get to one ball, and which is still real to all of us. What would be an image to get this? Because this seems like something else, right?
I think one way to think about that is to say, at least for the distinction there, right? In relativity, yes, we found that space and time are relative to the reference frame.
Yeah.
Different observers in different states of motion will assign different, say, times and positions or different lengths to objects, or two objects that are simultaneous in one reference frame will not be simultaneous in another reference frame. But what happens is absolute. All observers agree on what are all the events out there in space-time. And you can, given your description from your reference frame, there's a way I can transform that to the description to my reference frame and back again. And in these kinds of situations, it seems now that we can't do that, because now we're finding that the events themselves are relative. And so no longer there will be a way to transform from one quantum reference frame, if you want to put it that way, and back again. Although using loosely the word quantum reference frame because it has different connotations, right?
Yeah, and to just be very clear, Eric, I think people watching, when you say quantum reference frame, might go into a many worlds sort of thought here. Oh, we have, with Einstein gave us a block universe, and then quantum people know of the many worlds interpretation of quantum mechanics. But this is something different when we talk about a quantum reference frame in your line of work. It's not going in the direction of a many worlds interpretation, right? That everything that can happen happens, and I'm just sitting in a different branch of the wave function, the universal wave function.
So like I said, I use the word loosely here, because it has different connotations in different technical terms.
But do you get the misconception I'm hinting at? Because people watching might make that step. Say, oh, that's many worlds sort of.
But that's one possibility.
Okay.
So now the question of how do we resolve this theorem, right? How do we make sense? And we're talking about the possibility that absoluteness of observed events fails. And one way in which it can fail is exactly like in a many worlds interpretation. And then that event might be relativized to what is called a branch of the wave function. What is describing the universe in that picture is not just one four-dimensional space-time with all the events collected there, but a branching universe. And then relative to this branch, the observer saw one thing, relative to that one is another thing. So that's one alternative, but there's different ways you can try to think about that. And another alternative is also to reject the other assumptions, right? There's different interpretations that will reject locality, for example. Boy mechanics will say, no, there is one universal shared reality, but there is no local interactions between something that's happening here and something that's happening there. When I make a choice here, it does instantaneously affect something at a distance, even though we cannot use that to send a signal fast and light. And that's one of the sort of problematic.
Yeah,
I think it's really instructive to make this comparison to relativity theory that you also alluded to, because if I, for example, take general relativity, I also have the situation that different observers may actually see completely different things, not contradictory ones, but for example, if I look at a black hole in general relativity, then there's an observer who sits outside, and for him the black hole has an event horizon, and there's no way he can talk about things inside. But there are also other observers, for example, a freely falling observer who actually crosses the horizon, and for him everything looks very different. There's nothing going on at the event horizon, there's nothing special there. So we have already two observers who would describe the situations very differently. And this is just in general relativity. So it's not only that they have a different coordinate system in the sense that there's a translation of coordinates, it's also their coordinate system covers different parts of spaces, so that one outside simply cannot talk about stuff going on at the inside.
That's a good point.
And so in quantum theory, it now seems like things go even further. As in a sense, one could say, at least in general relativity, we can say that in certain patches, if the coordinate systems overlap, we know how to transition from one to the other. And because of that, we could actually come up with this view that one generally has, that one has a manifold of space-time that one could in principle look at from the outside. Of course, no one has this outside view, but we can just construct it as an object, which somehow reflects the fact that there is still some, let's say, intersubjective agreement between the agents. So the fact that there is a space-time manifold is for me just an indication that in general relativity we still can combine the different views and find a kind of perspective neutral picture of the world. Mm-hmm. Now this seems to fail in quantum theory. We have at least not found a way to find this like common perspective that, or one could again try to call it neutral or perspective neutral kind of description of what's going on, because we don't get, and maybe it's impossible to get, a description from which we can then get the view of everyone. Mm-hmm. That's one way we could again phrase the no-go theorem. So something like the space-time manifold in GR is not possible in quantum mechanics. So
this helps in understanding it. And Caslav, to move on to you. Yeah, please reflect or add.
No, I would like to stay on this similarity and dissimilarity with the GR. Like, as was told, we have this coordinate dependence. It depends on the reference frame, what we see, and different reference frame in GR. And that's why people then in GR came up with coordinate independent notions, like curvature. And then they assigned reality to these things that actually do not depend, that are common on invariant quantities. And that's the way, how can they transform from one to another. And as Renato just said, we are missing this thing. Usually what we have as analogy in quantum theory is something which we say, unitary transformation. This is exactly a transformation that transforms from one reference frame into another in quantum mechanics. And it works. Like probabilities that we obtained are invariant. After all, there are a number of clicks, you say. And as long as we share and we agree what the clicks are, we will count these clicks, and it will not depend in which reference frames we are. Now, the extending Wigner's friend scenario is a little bit different. And the maybe easiest way to see is that the friend who is inside has the possibility maybe to see two outcomes, like spin up and spin down. Whereas, and the description that friend has is one of those, but there are two possibilities. Yeah? Whereas the Wigner who is outside has just one and the same description. This description of this entangled state. For him, no measurement has been performed. He has not this information. And so you see that there is two things for the friend and one thing for Wigner, and you cannot combine with one unique function 2 points.
And please help me understand that there are two things for the friend, because I thought then the state would be already collapsed in one.
No, you're right. I'm not precise here in the language. I was just saying that there are, for each individual run, for each individual person, there will be one outcome. It's one outcome for everybody. I would not even know what it would mean, two outcomes for one person. I'm just saying that the totality of description of this situation allows one or the other outcome. And then it's not easy to transform, or we would say there is no unitary transformation, that these two possibilities will transform into one possibility for Wigner, because Wigner has one static outcome in ideal case. In
general relativity, though, we know there's not this God's position. We can sort of create that obstruct through mathematics that bring back sort of a unitary underlying structure that accounts for these different the different experience, different realities observers have. And now the problem in quantum, how I get it from Wigner's friend experiment, is that you have to draw a line and who's inside the box and who's outside, right? And is there a way to clearly do that and to know if we're entangled here or And of course, on a particle level, we know that. But I mean, if we think about this question.
I think this is still, a subject of investigation. There is some uncomfortable situation that in everyday life, even as a quantum experimentalist, but not in Wigner's friend situation, we are used to learn from other people what they have done and combine this knowledge with our knowledge, or we combine our knowledge in present from something which we experienced yesterday. Now, if there is some Wigner type interventions between the past and the future, or between different observers, these no-go theorems suggest that we should not do that, or there is no compatible way to do that. But how should we know in advance? I don't know the answer. There is, of course, the formal answer, in which if somebody is doing something with my brain, I should be careful, because all these experiments really influence also my memory. And it's a manipulation also, not on the entire laboratory of mine, not only about my system, but also about measurement apparatus, and after all, also about my memory. I intentionally avoid consciousness. It's a slippery business. If I make just kind of side remark, Danny Greenberger, one of the founders of Greenberger-Horn-Zeilinger theorem, said once, we know nothing about quantum, we know nothing about consciousness, so obviously they are connected to each other.
I know that one, yeah.
So what I want to say is that maybe this demarcation line is, which I cannot operationally now justify, is the moment when I see that my memory is subject of some future measurement, or I can judge that this will happen.
Yeah. And Eric, if we go to sort of the ontological options on the table to make sense of it all, sort of the different interpretations of quantum mechanics, sort of, and to all three of you after Eric, what option do you find most compelling, or you think there isn't one interpretation that makes sense at the moment?
Well, I don't want to pass a judgment on what I find most compelling. I'm more interested in knowing what the options are, right, and rule out the ones that are inconsistent.
If you could sketch the landscape from your...
Let's sketch the landscape. I'm not going to pick a choice. There's different people who have their own opinions for why they might prefer one or another. So on the side of rejecting absoluteness of observed events, one option that we discuss is average, the many worlds interpretation, right? Then the event is relative to a branch of the wave function. There's still some difficulties in that. All the interpretations have difficulties, right? But that's one of the alternatives. There's an interpretation also on that direction, which is QBism, in which it is relative to the observer. It's a lot more personalist in the sense that it's really referring to an agent that's performing an observation and having an experience. There is another called relational quantum mechanics, which is also tries to be in between many worlds and average, but there's also some difficulties in making precise sense of that sort of formally, which hasn't been fully well characterized. But the idea is to try to make it relative to a system, but not necessarily agents, conscious agents, right? That could be any physical system in principle, but without postulating the existence of all these parallel realities. Okay. Now, that's one alternative, rejecting absoluteness of those events. Another alternative is rejecting locality. The best developed, well-known case there is Bohr mechanics, in which there is a shared reality, but a choice that I make here can affect something instantaneously at a distance. On the side of rejecting, there's another assumption, which is assumption of free choice. The assumption we can make choices that are a priori, in principle, uncorrelated with the experiment. It's similar to the choice, for example, how do we make, randomized controlled trials of a vaccine, right? We randomly assign the vaccine to a number of patients, and the assumption is that I flipped a coin to choose whether or not I give you the vaccine, and the coin is uncorrelated with any factors that may influence whether or not the vaccine works for you. Maybe you have some genetic factors that would influence whether or not it works for you, but the coin is completely uncorrelated with that. So that's the assumption of free choice. It's not necessary that there is some free will in a strong metaphysical sense. So in that option, there are no well-developed theories that really do that and reproduce quantum mechanics fully. But there's research programs attempting to do that. One of those goes under the name of superdeterminism, in which these choices would be determined by some factors, which also would determine, say, in the case of the vaccine, your genes. But there would be some sort of common cause between. That's one possibility, but it's hard to work out a theory of the kind that.
And in a Bell test, that would mean that it seems as if Bell inequalities are violated, but there is something making that happen.
Right, exactly. The question that it would seem a little bit conspiratorial, right?
Yeah.
There really isn't any sort of non-local influence of any kind, and everything is happening normally, classically, but somehow, whenever I give you the vaccine, it turned out that you had just the right gene that would make you cured. So it wasn't the vaccine that cured you, right? It sounds like a little bit of a conspiratorial explanation. How to make that non-conspiratorial is very hard to see.
Yeah.
But logically, it's an open possibility.
And those options you sketch, if you had to put your chips sort of make a bet.
And just to think, there's another which is kind of it's a different flavor, but that technically goes on a similar direction, which is retrocausality, where a choice now can affect something in the past, but via the light cones still. So the goal is to try to do in a way that would maintain at least some sort of compatibility with relativity. But again, we don't have a well-constructed theory of that, but that's a logical possibility as well. In terms of options available, some of the others are better formulated, but again, all of them have some problem or another.
And yeah, as you said, you don't want to commit to one as most compelling, but is there one you think if you had to place your bet, you'd say, okay, most probably I go for this one?
Nope.
Okay, clear. Renato, you?
No, but maybe I should add that
please.
There's a distinction between the types of thought experiment we were proposing.
Mm-hmm.
And one of the distinctions is that, for example, in the version I have, there is this option of like giving up the assumption of free choice or locality doesn't exist, because in this experiment there is no choice. There is another assumption, though, which has to do with the transitivity of knowledge, basically saying that if I know that you know something, then I should also be able to promote that knowledge to mine. So it means that if I trust you and you're a good physicist and you write the book and I read that book, that I can use the facts that you wrote into this book. So that's an assumption, but that's why, from my viewpoint, if I look at the thought experiment, that I was considering the, let's say, categorization of the options is a bit different. But my conclusion is that none of the existing interpretations gives a satisfactory answer of what happens in this paradox. So I'm pretty much convinced that the answer lies somewhere else. It's outside of the collection of interpretations that are currently available.
Mm-hmm. How's that for you, Caslav?
Well, I also have no definite favorite, but I know what I would not go, which road is not fruitful for me. And these are the interpretations that are mentioned now, like superdeterminism and many worlds, and also Bayesianism. And the reason is that none of them can be wrong. These ideas alone do not restrict in any sensical way our physical theories. Because superdeterminism, from superdeterministic idea, you can derive any correlation, not only quantum correlation, anything, whatever you want.
Yeah, whenever you encounter weirdness, you just say there's an underlying common cause that determines this.
Yeah,
Yeah, and you can go on forever with that.
But you know, for example, that quantum mechanics doesn't violate Bell inequalities maximally. There is some bound. So you have to add something to these interpretations to get the quantum bound. And that what you add to this interpretation would be far more interesting than the original idea. And this is the same for many worlds. Like, I'm not talking about a Varietian many worlds in which you embed the quantum formulas, but just the idea of many worlds. Everything could, if something could happen, will happen somewhere. I mean, there is no restriction to this idea. So it's not a fruitful idea. Bayesianism is also, Bayesianism is a way to understand probabilities. But which probabilities? Classical, quantum, general probabilistic theories, everything you can embed in this. So somehow I don't feel these ideas, without supplementing with something which I said is more interesting than the ideas themselves, are fruitful. What I feel that will remain maybe, it's something about relational aspects. That's kind of privacy of our events maybe. And also what I would like to be, if I have any idea about what's the solution is, I would like to be able to go to my experimental colleagues and convince them that the idea is correct or that the other alternative ideas will not work. And in that sense, I'm very much operationalist. Or if you want, some sort of Copenhagen flavor, combined with the relationalism, and also combined with idea that theories are somehow closed. Even probabilistic theories are closed in a sense that at some point I talk about data, that's the operationalist part, I get probabilities, but I don't have a division between the systems and the apparatus that will collect this data. I would like to allow somebody else put the Heisenberg cut somewhere else. And even, so the theory is closed in a sense that it's universal. Everything could be considered as a quantum system. But in order to make sense about it, I should have something outside of that, measurement apparatus to collect probabilities. It's just that what I consider as a measurement apparatus is not a measurement apparatus for somebody else. And then we are back exactly where we started, because this is a Wigner's friend.
And it's an infinite progression. And what about sort of the divide you often hear when it comes to interpretations of quantum mechanics between ontic quants and epistemic quants? And I've got many worlds. A Retian view is more ontic, as it sees the quantum state superposition as something real out there, and then you end up with these worlds with all these facts taking place. And the epistemic ones, so Bayesianism, quantum Bayesianism, says no, it's just really about our knowledge about nature. Do you find that
more subtle than that, because
useful? Those words, just epistemic and ontic, does that still make sense to you?
I would say it's a little bit more subtle than that. When you say knowledge about nature, there's a class of theories that are called psi-epistemic theories, in which the wave function corresponds to knowledge about something that's out there, about the ontology.
Yeah.
But there's something that's definitely there, and the wave function is just like a probability distribution, like I'm giving something what I know about it. But QBism is not quite like that. It's not just saying the wave function is just information about whatever is already out there. It's information about what you should expect your experiences to be if you perform this or that experiment.
Yeah.
But the fact that you are performing an experiment, that you're taking an action in the world, is important, because in QBism you can, that action participates in the creation of that experience.
Yeah, that's what we talked to Chris Fuchs today, right. And that's also what I still find difficult, that you place your ontology on the measurement itself, in a sense, right? He wants sort of an ontology of measurement, he said in his talk today. So
yeah.
And what you're saying, so when you say epistemic, you say, okay.
I'm saying in the sense that sometimes the distinction is made. There's some technical sense in which the distinction is made, referring to what's called an ontological model. It's a certain way of certain framework of describing models that attempt to reproduce quantum mechanics with some ontological description. In that context, there's a distinction between the wave function being ontic, describing something that's out there, or being epistemic in the sense of the information about what's out there. But there's another sense, which is QBism, which is not quite that sense. You can say it's epistemic in some way, but then it just things a little bit confusing in terms of how the words are used. Because those psi-epistemic theories, they have essentially been ruled out. There's some no-go theorems and experiments that have been done that I've been involved with as well, which ruled out a large class of psi-epistemic theories, and sort of any alternative that's left is very, very uncomfortable. It's very implausible. So that particular form of epistemic theories are actually not available. So QBism is a different kind. It's not knowledge about what's out there with function. It's really knowledge about the potential outcomes of an action that an agent can take on the potential experiences.
If I may contradict something that Caslav said.
Please do.
I mean, you mentioned that QBism is not fruitful in a sense. And I would say, I mean, as I mentioned before, I don't see any of the interpretations that are out there as going to be the solution. And I would even agree first with the statement that, of course, at the end, we want something that can be wrong. So we want to be able to go to an experimentalist and verify it. However, I think the ideas that some of these interpretations convey, the philosophical ideas, are sometimes extremely inspiring and good ideas. And I think in particular in the case of QBism, QBism is, let's say, I would say the interpretation that takes the idea that things are subjective extremely seriously, even more seriously than most other interpretations like the psi-epistemic that say knowledge is important. They really are kind of, in a sense, more consequent about the idea that maybe the facts or the absolute facts are not a good concept in the way we thought it would be. And in that sense, I see a lot of value. I don't see it as the solution, but in the idea, I see a lot of value. And at the end, I think what is missing, and here I think I agree again, is that this approach should still give us a way to do experiments. If we have different agents, so QBism is basically a single agent theory, and if two different agents disagree, they just disagree, and it's fine for a QBist. And that's, I think, a problem, because that makes it impossible to really check things. If I go to an experimentalist, I have to compare my predictions with his and so on. But as an idea, as a philosophical idea, I think I very much like the approach. I said before, like we always learn again, things are subjective, I think. And the lesson was really learned many times. There are countless examples, let's say, Hawking radiation, or let's say even Unruh radiation. It exists for an accelerated observer. He sees particles, but an inertial observer doesn't see any particles there. So the notion of is there a particle or not is observer dependent, even without any Wigner's friend. It's just an accelerated versus a non-accelerated observer. So we again see that things we thought are there, is there an electron or not? We should be able to decide, but apparently we cannot do that in an absolute way. And I think this idea is best conveyed by QBism, although not even consequent enough.
Yeah, there's this renaissance of phenomenology. I always struggle with that word. That because it so resonates with what you guys are doing. Are there philosophers? I know you're physicists, but that you think, this resonates with me. For instance, when I hear you guys talk, I think about Leibniz. So we have different nodes, and somehow it's highly subjective, but it's also relational, and then you get to something. So that's what rings with me. But are there sort of philosophers or thinkers that capture sort of what you are hitting on in your work? I mean,
may I maybe just explain in relation to QBism? I think that there was a very important historical role, I think, of QBism, because it was the first, I think, somewhat complete or coherent, better than complete, subjective interpretation of quantum mechanics. And it somehow contribute to stop the dictatorship of realism. But as such, as usually what historically happens, every progressive idea, if you keep going that path, without modifying starts to be retrograde. And that's what I feel I experience right now. And the reason is that this idea alone is not sufficient. And when I was thinking about what I find useful is, are the ideas strong enough that they will narrow down the set of possible theories in the landscape and perhaps even single out quantum theory? And then I feel that it's not enough. In a very similar way as many worlds or superdeterminism is not enough. But if somebody would ask me where my head will stay among three of them, and not that it's my favorite, but among three of them, that will be certainly QBism.
Thanks, and thanks for this nuanced view. Getting back to sort of where to draw the line between what counts as an observer and what as a system. So I'm now starting to get that within quantum physics that's not so clear, and you guys call that a Heisenberg cut, right? Where you make that. And what criteria do we have or theory of where to make that cut exactly between observer and system?
I see the cut. I mean, actually, we had a long discussion over lunch, so this is not a settled question. But I see the cut as a choice I make when I analyze an experiment. The choice has certain constraints, but let's say I walk into a lab of an experimentalist, and the experiment has already been done, and the experimentalist asks me to analyze it as a theorist. Now I have to make certain choices. Maybe the experiment involves centrally an ion that was measured. And now I could say, okay, the ion is the system I really want to study, so let me just put that or define that as the quantum system I want to analyze, which now means in this language, I put the Heisenberg cut around this ion, everything that is outside, I'm not considering as a quantum system. Now I could also say, actually, I understand this little detector that measures the ion very well. I want to model that also as a quantum system together with the ion. So I include everything into the domain I'm describing with my quantum formalism. And I could again do the analysis. Now the question is, which of these two ways of analyzing the same experiment is the correct one? And I think there is an old answer. Actually, in the book by von Neumann, you find a whole chapter about like these different choices of where to do the measurement. And the commonly accepted answer, which he even proved mathematically, is it actually doesn't matter if you are careful enough. And being careful just means, of course, there are some constraints. And the constraint on the one hand is, if, for example, I have some quantum effects that I want to consider, let's say some superposition, that system, of course, has to be inside the domain I analyze quantum mechanically. The other constraint is that the final observation has to be some observation that I can think about, so I should not myself put into the quantum domain. So I'm kind of outside as an observer. But this is a very, very weak constraint. So I have a lot of liberty of where to put the cut. And I think in the argument, at least in the version I have, and I think we hear there are also some differences and in some extension that I developed actually with Lydia, one would say the idea is that we actually assume about quantum theory that we indeed have this freedom given the constraints, and we check what happens when we have this freedom. Do we get contradictions? And so that choice, or the fact that we have this choice, plays a very important role in our assumptions. So someone could say, that's the wrong thing. Maybe there is a rule that defines where to put the Heisenberg cut. But if you open a textbook on quantum mechanics, you will not find a rule. The textbook just says, let's analyze the hydrogen atom, and then apparently the cut is around the atom. But this is just maybe in an exercise of the book, even like we look at this system and now, but it's not, there's no, let's say, physical law that you can find in any quantum mechanics book that says, this is the way you have to choose the cut. So in other words, at the moment with the currently developed formalism, we have no other way than to assume it doesn't matter, because otherwise, obviously, we would need some rules that tell us how to choose that.
This sort of brings me with a sort of roundabout to my final question. As you mentioned, von Neumann, wasn't he still into a consciousness causes collapse interpretation? That was, of course, a long time ago, before experiments now done. But Eric, to you as a sort of closing question, how does quantum theory, how does it relate to consciousness? What do you think? I mean, Wigner's friend talks about conscious observers. We cannot yet perform those experiments, so we cannot say anything experimentally about it. I know we don't have a definition of consciousness yet, but what are your sort of just thoughts? And I won't pin you down on it, but I'm just curious to brainstorm a bit with the three of you about it, as our audience really finds that so interesting.
Yeah, it's a good question. The Wigner's friend thought experiment doesn't necessarily need to involve a conscious observer. That's one thing to say. It requires an observer, right? The question is, can there be an observer that's not conscious? Well, it could be, we might say that an observation in the required sense might occur when there is a collapse of the wave function, supposing that it is a sort of objective process, right? So that's one of the alternatives that we actually didn't discuss much, which is that objectively there is a collapse. And so that would mean that if we perform the experiment with a genuine observer in the box, the inequalities would not be violated. Would mean also that quantum mechanics fails at some point, right? Which would be a very surprising result. That would mean that quantum mechanics is not universally applicable at the level of observer. So that's one alternative. But if that alternative is the case, it might be that, some class of objects that are macroscopic or they have some properties which are not necessarily consciousness will act as observers in the required sense. There is a possibility that it could be consciousness itself which is required, although there is no developed theory along those lines that would explain in what way that happens. But it's one of the possibilities. It could turn out that the experiments go that way. Again, unlikely, I would say a priori, but it's one possibility as well. Now, I think ultimately, where that ends up touching the question of consciousness is that the difficulties in explaining these phenomena, these thought experiments, are partly because we want to explain our observations, right? Ultimately, we want to explain our observations. And if we think that there is a conscious observer inside that box, inside this experiment, our theory would be incomplete if it wouldn't explain somehow or account for what it would look like for that observer, right? So that there being an observer there makes it necessary, it seems, that the theory would have to account for that. Otherwise, the theory is failing at this primary goal of explaining or accounting for our observations.
Thanks.
Caslav often hit the table, and then I think this is a good example because I would completely agree with what Erik just said, that what we want to understand is why do I have this perception? If I have a perception, that's obvious. I mean, I don't need to understand what consciousness is. I have this perception. And I want to link the physical theory that describes the world to this perception. So what else should I want from a theory? It should at the end match with things I perceive. So that's somehow the goal. And in that sense, one could say there is certainly a desire to understand if one now means by this perception there's some consciousness involved. One wants to understand consciousness. Having said this, and now, as being a physicist, I have to admit I cannot say anything about consciousness. So I think it's certainly true what Caslav said before. At least I don't understand anything about consciousness. But now I think the interesting thing about these Wigner's friend thought experiments is that we talk about observers or agents. And if you look into these theorems, they make a very clear definition of what are the requirements we have on agents. There may be different in our theorems. Like in one case, it's about some kind of complexity in the sense that an agent can kind of behave like we do or is indistinguishable. In my version of the experiment, the requirement is that an agent is an object that has the information processing power to actually use quantum theory as a theory. So that's a definition. I mean, I'm not saying that this is really a definition in the sense that it's a necessary insufficient criterion, but I would say I at least think I can apply the formalism of quantum theory, and that's just the condition I now need when I do the experiment. So if someone does the experiment and he can do it with a machine that is able to apply the formalism of quantum theory, and this machine plays now the role of the agent in the experiment, then I'm happy.
You're satisfied. Yeah.
So in that sense, I think we can really now make this connection to agency. Whether this is now really consciousness or not, again, here I cannot say anything, but I think we should make this step and say it's actually a physical question to bring in the agent into the picture. And this is often criticized, in particular if one talks to older colleagues. They say there's just no role for the agent. I think it's very important to admit that at the end, I want to understand what happens here.
Yeah, and I think you can also agree then with Marcus Müller, who we also talked to, who says it like, what do I see next? That is sort of the crucial question at play, right? And Caslav, to you, already many times referred to the knocking. You can do once more for us.
No, I think I would agree with both of you, of course, that like hitting the table is also a part of the quantum theory. It's the way how we predict what will be next, as Marcus said, is conditional on what was the last outcome, to be able to say something about what will be the next one. And we have this enormously powerful theory, a quantum theory that works in all these circumstances. But now we are put in the situation in which two observers do the same, and each of them claim that is an outcome, and now I should, based on this outcome, predict what will happen next by this powerful theory. And we run into the problems, partially, if we want to combine these two worlds. So it's really, I feel that one part of importance of this experiment is that it goes beyond Bell's theorem in a very sophisticated way, and exactly in the way that particle cannot communicate, or for particle, we first don't know what it is. Particle does not use this for any predictions future. So it's really like a kind of proof of principle, but I'm not surprised that it goes through. And I feel like if we would be able, either through the machine or the real human, to tell us, I heard hitting of the desk in my laboratory. I don't let you where I hit it. This is the outcome, what happened. And I know that, and I do my part of my side. I feel it's a very strange tense to accept that although you told me that there is something happening, I should not take into account in my understanding of in my laboratory, in my bubble. And this is very, very hard to swallow.
It's disturbing. And I'm going to wrap this up, and I'm very thankful for this conversation, but just a reflection. I recently also I interviewed Sir Roger Penrose twice, also on the possibility of conscious AI, etc. And you must be familiar with his work, and perhaps also with his theory of consciousness, which you can say a lot about, but I do think he is doing interesting work, as are now coming some empirical findings in favor of it. But in the end, for him, it seems to me that he would still place consciousness at the end of a causal chain that starts with a sort of just the classical story of we have the Big Bang, the evolution, and then the Wheeler picture, and then but for him it really starts still with that Big Bang picture. And just as final question to the theory, do you think that if we would come to a theory, and hopefully physics can sort of help us better explain consciousness, do you think it will be in that line of thought as a sort of an epiphenomenon at the end of a chain, or you think it's a bit more complicated than that and it could be more primary or intertwined?
I'm sometimes very sympathetic with what Carl von Weizsäcker called Kreisgang. It's a circular yet coherent argumentation. And very often also in the discussion, for example, in the interpretation of quantum mechanics or in the relation between classical and quantum physics, people like to cut the chain and tell the story, this is the beginning, and there you end. And then there are people who will say, well, quantum fields, this is the most elementary things. And then in some limits of coarse graining observation, we come up to the classical physics. And then there is a Copenhagen maybe, who will like, oh, no, I mean, we cannot even say anything without classical apparatus. All clicks or all quantum phenomena is just a relation between our classical apparatus, preparation and the measurement. There is no particle, it's just clicks that I try now to coherently interpret, and then I come up with the idea of maybe there is a particle, but there is nothing there, first. And then I felt always that both sides have right in a certain sense, and that we don't need to make this choice. And if there is a coherent picture in a sense that in order to define the state, I cannot define the state without referring to something external, as Renato said, and this external is usually classical and quantum, then that's a part of the story. But this doesn't also prevent me to think about the measurement apparatus as being built by some maybe particles that have state. And then you can say, but which state? Well, state that are defined with respect to the external measurement apparatus. And I'm not, this is a circular reasoning, but it's coherent, and I have nothing against that kind of solution. I'm not answering your question directly, but I think that's the analogy that I would like to, with which I can live as a
I get it. And but just the image that pops to mind is that the U of Wheeler,
it's the Wheeler. It's the same
but you
as
want to
Wheeler.
make it circular. You just say, I don't want to pick either of one side. And do you have anything to add to that, Eric, Renato, as sort of a final thought?
I think I agree with that. Generally, I would say any picture that would just put the observer at the end of a chain would, for me, be going the wrong direction, because I think what we learn is really the observer or the agent plays an extremely important role. So it's not at the end of a chain. It's maybe circular or even, let's say, more involved in the sense that everything is at the end, at any stage relative to that observer. So I think we should just do physics in a way that takes the idea of observer-agent dependence, or however one wants to call it, much more seriously than we do it today.
Thank you. Yeah. And Eric?
Yeah, so I think, for example, just to riff a little bit on the Wheeler mentioned the observer participancy, right? The way that I like to think about what I think Wheeler is saying there is something along the lines of, yes, the fact that we're performing an observation now, and the choices that we make in whether or not to perform an observation, whether or not to open the box and ask the friend, what have you seen? Right? Have you seen a definite outcome? And then the friend comes out and says, yes, I have. That observation that we make now may not only, you don't need to think that it creates those events now, but it also reaches back into the past in some way and makes it real relative to you and to that perspective from which you are observing that event. And so, yeah, the fact that there is an observer at the end obtaining that information and in some sense making it real relative to that observer may not have even created the observation for the friend that was inside. The friend had his own observation, but it's connected to the outside observer now. But it makes part of one coherent history that reaches back in past. And I think that the difficulty there is to trying to find a language even and trying to make sense of that as being a shared reality, but not in terms that you are literally affecting the past, but in terms that it is it's coalescing the the realities become coalesced in a certain sense. But then I think the different perspectives are important for each observer, I think, in the sense that if we take seriously that there are these different perspectives, right? I want to believe that there is a perspective from the friend inside the box. And I want to not say that I'm that is only real when it becomes real to me. But the fact that there are perspectives to be accounted for at all, I think it's an important part of the problem.
Thanks for all three of you on reflecting on that question of consciousness. And we recently at our foundation had a conference about time and minds. We were reflecting, and that was more about Einstein. But of course, the difficulty of how to account for mind in our universe, for something which what it is to be in this universe, like how philosophers like to put it. But then Lee Smolin surprised us in the sense that he also ponders on this. And in one of his lectures, he tried to come up with a way to account for qualia. That's sort of the term. It's a more neutral term than consciousness, right? It's just the contents of perception. And in those contents, we see a defined states. We never see a superposition. So how can we get to this qualia? And in that presentation, he at some moment said, the universe is nothing but a collection of partial views upon itself. And that to me was just a very beautiful way to summarize it. And in a way, it feels as if you are in the same space as Lee when it comes to that. So it's these partial views upon itself, because it's all part of the universe, and that's it. Does it resonate with you?
Yeah, although I think the consequence of these theorems, if you want to keep locality and so on, would be that the partial views cannot be put together as one God's eye view, that the partial views are in some sense really incompatible.
It's much more fragmented, or even incompatible. As a stronger. So somehow this quote sounds like a very united picture of reality, even if it is somehow self-reflecting. But there is, at least from these theorems, much more something like fragmented, perspectival.
I would not necessarily call it fragmental, because I could also take the viewpoint that, let's suppose that things can really not be put together. So maybe there is nothing to be put together. Maybe there is just my perspective, and I should just accept that. Now, also maybe coming back to like the question, what is consciousness? Still, I don't know what it is, but I could say it's certainly a starting point. It's not something that comes out of the world, because I have this perception. That's at the very start. That's the most certain thing in the world, is that I feel this. It's much more certain than that atoms somewhere out there exist. So for me, this is a starting point. And now maybe we develop this desire to kind of find a common picture, which seems fragmented. But maybe I should just start from there and say, there are these perceptions that I have, and that's how we should start with physics. So it puts me in the center. This sounds now, again, extremely subjective. But I think that's a viewpoint that hasn't been really studied recently, at least. And for me, this is extremely promising, at least. Or the theorems we have, the insights point at that this is at least an option. And if you follow this option, all these ideas about like things like our perceptions are emergent from an underlying world would just not even make sense, because one would just start from this as the basic thing, and all the rest is.
And this is classic Descartes before he turned sort of dualist, right? You say the cogito ergo sum, that sort of as a primary thing, and which makes me work for our foundation, Essentia Foundation, because idealism. I don't want to commit. Cannot say it's true because I have no way to prove or falsify it. The only thing I can say, it feels as a very nice working hypothesis to start from, and to try and then get to an objective component, because I don't want to end up sort of solipsist worldview. And in a sense, to thank all of you, what you put in the hard work. If we're trapped in mind or trapped in this universe, you guys are really putting the hard work not to jump to conclusions or weird stories about it, but to be rigorous and just test stuff. And I really appreciate that. I want to congratulate you with your award, and then I hope you enjoy that tomorrow. And thanks so much for this conversation, all of you. And thank you for watching this. If you like this conversation, please comment, like, and subscribe. And if you have further questions to either Caslav, Renato, or Eric, leave them in the comments also. We can pass them on or organize another debate perhaps. And we hope to see you in one of our next videos on the foundations of quantum mechanics. Thanks. I hope you enjoyed this conversation as much as I enjoyed having it with these great physicists. And I can only say that at the moment of recording the interview, I still very much struggled to just get my head around of what they were actually saying. And for that reason, I also include their full lectures right now for you to watch. I do have to apologize for some technical issues we had whilst recording, which means that the audio quality at some points in the lectures is not that good. It is understandable though, but just not that good at all moments. I have included a title in top screen where you can see when audio is bad and when it will improve again, so you know exactly where the good and bad spots are. And because this is such a big topic, please drop questions to us about other videos you'd like to see on these sort of extended Wigner Friends thought experiments. For now, I'd say enjoy the lectures, and also below in the description you can find links to the scientific papers, the papers that won this Ehrenfest Best Paper Award.
Dear colleagues, dear guests, it's my great pleasure to welcome you to this part of the conference and present the Paul Ehrenfest Best Paper Award for Quantum Foundations, an award that honors significant contributions to the foundations of quantum mechanics. The Ehrenfest Award conferred annually to the authors of the work published within the past 5 years that has made a considerable impact on the field. Both theoretical and experimental works are eligible for this award, and our aim is to raise awareness and importance of quantum foundations while recognizing the vital contributions made by researchers in this area. The prize is named after Paul Ehrenfest, a brilliant physicist of the early 20th century, known for his profound contributions to quantum theory, statistical mechanics, and gravitation. So without further delay, with some delay, so I'm very proud to introduce the winning trio of papers for 2023. A no-go theorem for observer-independent facts by Brukner. Quantum theory cannot be consistently described by the use of itself by Fauching and Renner. And a strong no-go theorem on the Wigner's friend paradox by Bong, Utreras, Alcon, Gaffari, Liang, Tischler, Cavalcanti, Pride, and Wiesmann. So the members of the selection committee of the Paul Ehrenfest Award for 2023 year were Borivoje Dakic from the University of Vienna and Ikoki, that's me. Philip Goyal from the State University of New York at Albany, Philip is also here. Lucien Hardy from the Perimeter Institute in Waterloo, Canada. Marcin Pawlowski from the University of Gdańsk, Poland. And Urvashi Sinya from the Raman Research Institute in Bangalore, India. So the committee has concluded the following. In these papers, the authors extend Wigner's famous thought experiment by combining it with aspects of Bell setup, thereby constructing a variety of closely related no-go theorems. These theorems challenge the applicability of quantum mechanics to arbitrary physical systems, including macroscopic objects and observers, paid with various assumptions such as the absoluteness of measurement outcome or certain locality assumptions, some of which are weaker than those in Bell's theorem or Cohen-Specken theorem. As a result, these theorems provide new challenges for the interpretation of quantum theory, forcing us to make some hard choices in our conception of quantum reality. So dear Caslav, dear Renato, dear Eric, congratulations to you and your co-workers. I kindly invite you for the award certificate, and Flavio will take some pictures. Renato? Okay, so now we will proceed with a rather short presentations by all three works. So I will be a chairman. I kindly ask you to keep your questions for the end. So after all three speakers have their presentations. So Caslav, you will start, please.
Okay. So, good afternoon, everybody. Let me start by thanking the award committee headed by Bori, and Philip is here as well, and all other members for selecting the three papers for the award Paul Ehrenfest 2023. I also want to extend my thanks to two further persons who nominated us for this award, David Schmidt and Matt Leifer. I don't know where you are. Matt is there, and David is over there. Thanks. That's a great pleasure and also an honor to share this prize with the colleagues of mine, with Eric, Renato, and also co-authors of the two papers. So I decided to put the title, What Happens, for the talk today. And so let me start with an experiment. And that is like, I will hit this desk, I hit even harder, and you hear this. And we can maybe agree that this is an event, that this is something which really happens. Really happens because you have done it in the past, you know how it feels. And we shared the sound, and we have immediate experience of that. So maybe there are different approaches to what an event could be. Maybe people who are, from an interpretational point of view, a little bit more on the realistic side will say, well, this is not the elementary event. Maybe it's composed of many other elementary events, but no doubt it's a composite event, and it is an event. It's immediate experience. Those who are more on the Copenhagen side, maybe they will say, oh, this is the thing that we start with. That's the elementary Borean phenomenon, and that's his event. So in entire my talk, I will talk about those events, and I hope that we have no disagreement that they are happenings. Okay, now today in the morning, Anton Zeilinger said that he has a very strong belief that no matter how complex, how large or heavy objects are, they will eventually be quantum mechanical, and we will eventually be able to show quantumness, given that we have enough funding for the experiments. Now, these two statements are quite distinct to each other, and what I want to show today, that if we believe in what Anton Zeilinger believes, we should maybe have an element to doubt that these events we can actually share among us. And even if I do it harder and I start to feel pain, you might hear these events, but not only that you will not share the pain, which you do not anyway, even just to imagine at the same time, from your perspective, that I share pain, that I feel the pain, that it hurts, combined with any events that you share, are not compatible. We cannot combine them in any logical framework. We cannot assign truth value to the questions whether I feel pain and you do something else. Okay, that's a long path towards that. And this seems to be quite disentangled statements. Now, the way how to arrive at this conclusion is to combine two elementary experiments in quantum mechanics, one of them being Gedanken experiment, the other one used to be a Gedanken experiment, it's now a real experiment. And this is Wigner's friend experiment and Bell's experiment. One done by Wigner, thought experiment, thought through, one 1961, the other in 1964. Now, what I want to tell you a little bit at the beginning is my personal path towards combining these two puzzles and towards the statement that I made at the beginning. So somewhere in November 2013, I was at the workshop in a beautiful place, Traunkirchen, Austria. Chris Fuchs knows the place very well. I've been discussing with Richard Hillier a lot about the meaning of the Wigner's friend. And somewhere at the end of this workshop, I had some vague impression that Wigner and Wigner's friend should have incompatible experiences, or should something was not fitting that together. Not only in a sense that there is ambiguity in assigning the state that they do, but something more deeper. And this idea crystallized very well so that I could present this in June 2014 at the Vienna conference. This was 10 years ago for the 50 years of Bell's theorem. But it was very speculative, and luckily I was forced to write down a proceeding for this conference, where you usually write the things that are very speculative and you do not dare to write elsewhere. And so I wrote this thing and submitted on arXiv in 2015, which was eventually published in 2017 in the proceedings. Now, it was not a surprise for me that there was no reaction. But seemingly, and almost no citations as well, but seemingly one group at that time read this paper, and I had one citation then coming in 2018, and that was Renner paper, where they cited me. And this paper got quite attention. There was a huge echo in quantum foundation community, but somehow my 2015 papers was still not read. And then I write another paper, which was rewriting the argument once more. Okay, you choose different words, you try to be more precise, that was 2018. So what I want to tell you, especially for young people, if you think that some idea is right, say it loud, say it many times. And just because of this 2018, I could got this award, because it was for the last 5 years. Okay, what is the path to the award? So, I said there are two experiments that are involved in this argument. One is Bell's theorem. There are many different readings of Bell's theorem. The one that I like is that the theorem assumes that the measurement you did not do would have had a definite outcome. So it has a flavor of counterfactual reasoning. And hidden variables are exactly introduced to determine joint probabilities, both for actual but also counterfactual outcomes. And now, the reaction to the relation of Bell inequalities could be that you should not do that. And Asher Perez nicely put it in the title of his work, unperformed experiments have no results. And I found a peace with this. And also I have some work with Anton that he mentioned, in which we claim that quantum systems contain finite information, and so they can answer only one question. They cannot have prepared answers to many experimental questions, which was somehow fitting in this understanding of Bell's theorem. Okay, that's one part of the puzzle. The another experiment that comes here into play is Wigner's thought experiment in 1961, where he considers two observers, one of them being, let's say, inside of lab or box, that's the friend, performing some experiment of spin, and having an outcome, getting an outcome, an immediate experience, just like that. It is a click of the detector. Now, upon observation, this observer will update the knowledge and will have either one or the other state. And this is very important information for any future experiment to be performed in the lab. On the other hand, if we think that this is really a totally sealed laboratory, one could imagine that there is an external observer for whom there was no measurement, and therefore this observer could still think about this measurement as just an interaction between two quantum systems for which he will write down a state. And this state is this entangled state because he doesn't know what has happened inside. Now, there was a very important variant of this experiment done by Deutsch in 1985. I don't even know if you have seen the change. The change from this to that is that he adds a measurement. And now, it's not only a description that is entangled, description to Wigner, this entangled state, it's more than that. Wigner can actually verify, confirm that from his point of view, this is an entangled state. And now, there was one element more in his paper. He said, not only that, the friend can communicate to the Wigner by saying, for example, dear Wigner, I have performed the measurement and obtained a definite outcome. So at that point, Wigner could think like, I have seen my outcome, and there is some evidence that there is a definite outcome inside. Is it not enough? Is it not enough evidences that assume that two outcomes coexist? And so by simply acknowledging that the friend preserves her outcome in the same way as he does, Wigner is almost compelled to introduce a hidden variable to determine the joint probability for both her and his outcome. So it's not only anymore about counterfactual reasoning. Why should I take care about counterfactual reasoning? There is an observation of both outcomes, admittedly by different observers. And that's exactly the moment where you can fall into the hidden variable trap. Namely, you can start to think that these joint probabilities exist. And you can assign, for example, some value to friend's outcome and some value to Wigner's outcome and say, well, there is enough evidences. I put and define the joint probability for these two. And this is a simple exercise, and let's keep this extremely simple and think just that the outcomes are binary outcomes that you have +1 or -1. And now you can think about, to denote the measurement result of Wigner in this entangled basis as X. This is the second digit in this binary pair, and the Z to be a measurement that friends keep measuring. And then you can think, okay, I assume that this exists, but whenever I want to say what really Wigner observes, I don't have, from the Wigner's point of view, I don't have access to both of them, so I would just assume that what Wigner observes is the marginal probability of this joint probability. That's one understanding of his entangling measurement. But then he can maybe do something else. Maybe Wigner can open the lab and, so to say, ask the friend what she observes, or look at the same measurement device as Wigner does. As the friend does. And then this, what now Wigner will see, does not necessarily need to be just the marginal of these joint probabilities, because by opening this box, you can maybe do something destructively on the result that there was before opening the box. So, in a sense, opening the box may disturb what the friend has seen. Now, these elements put together bring us to the Wigner's Bell scenario that was introduced in this 2015 paper, and in which we have two Wigners and two friends, and let's call it friends Charlie and Debbie, and Alice and Bob are Wigners on two sides. And then, by the same argument, in which, for example, friends can send out the messages claiming that they see definite outcome all the time, the two Wigners could come up with the idea that there must be a joint probability for all four outcomes. Hello? Two of them for Wigner and two of them for friend. Now, I want to make a next step towards the Bell's experiment. Namely, I want to define what two Wigners, Alice and Bob, can measure. And I say they can either ask the friend which results she observes by opening the boxes, or they can measure still the laboratory in entangled basis and introduce corresponding observables in quantum mechanical formalism. And now you have another element of the whole theorem, and that's locality. You say, okay, sure, asking the friend about measurement or opening the box can indeed disturb the result that was there before, but we assume that this disturbance is local. So asking the friend measurement can disturb only what the local friend has seen in the box, and nothing what is distant from this box, distant from this laboratory. This assumption and assumption about existence of this joint probability lead us to the Bell-type inequalities, which we know, if we believe in quantum mechanical formalism, we can violate. And so we can conclude that no opening of a box that disturbs only what the local friend has seen in the lab can explain the Bell inequality violation. And that's the end of 2015 paper. Not fully, technically. Now the question is what we can learn from that. But before I go into what we can learn from that, and what is written in these 2015 papers, I want also to say that there is a disadvantage or a loophole of the argument. And the thing is related with the fact that in some cases, in my theorem, I still assume that the results of experiments not carried out exist. And these are those cases when we open the box, let's say Alice opened the box, can disturb the Charlie's result, but in this argument, I still assume that there is existence of the Alice measurement, although she had decided, of the first entangling measurement, although she decided to open the box. So I see my theorem somewhere in between Bell's theorem and local friendliness, that you will hear later on, because this theorem gives more substance in the assumption why we should assume that there is these outcomes over there, at least in some subset of the cases. And there is this one setting in which all 4 outcomes are there. So you can think about all other measurements as some kind of a coarse graining of this small, fine-grained set of all 4 measurements. But however, there is this disadvantage. And this disadvantage was then turned into a new theorem, a wonderful theorem, which is called local friendliness, and Eric will talk next about that. But at that moment, I want to say that when local friendliness appeared, I was just amazed, because I thought that you can't go beyond Bell inequalities, that this kind of that this kind of disadvantage will be there, and was not convinced that you can overcome that, and that I was disproved. But I was not unhappy about that. So what you see here is a cover page of Süddeutsche, a newspaper in Germany. It says, "Unhappy Austria, a study criticized local friendliness." And it says also that the Austrians are the only nation that is more grumpy than Kuwait. You can think about this as a recommendation for our elections that are coming now on Sunday. So, what happens? That was the question at the very beginning. There are several possible paths. One possible path is a measurement for everyone. It makes no sense to consider the Franz apparatus as a part of Wigner's quantum system. In our papers, we call this non-universality of quantum mechanics, but I'm not sure that people who support this idea would like this name. And the prominent supporter of this idea is Wigner's Wigner's enemy. I think you see also the name of the badge. It's a Marek Żukowski badge. When I saw this, it came immediately to my mind. An enemy of your enemy is your friend. But since I consider Wigner and his friend not so great friend as Marek, I left this option of reply. So indeed, Marek Żukowski, Philippe Grangier, also I would call traditional Copenhagen, have this view that there is nothing after the measurement, that measurement is actually for everyone. One possible way to understand when I think about this as a realistic option is what Marek actually told in his talk, that the resources that are required to perform this experiment maybe exceed the resources that are available in the whole universe. So why should we care about that? That, unfortunately, has to be proven. And it could be that in this proof we overcome the possibility to do something with the finite resources. And at the end, the possible answer towards this exit is that there are collapse models, and I've never thought that Marek will be in the group of people who support collapse models. That's a moral. You do not, but from that point of view, you are not far away. Okay, what would be the other option? Other option would be that opening a box has a non-local effect on what the distant friend of Wigner sees. It's some kind of non-locality, and Bohmian mechanics or some other non-local theories go this way. And it's very much related to Nicolas Gisin's signaling question mark title. And we in the group, Veronica and myself, play around with that. And we thought about the friend, or modeling the friend, as having two different parts of memory. One in which the friend stores the result, and the other type of memory in which we only remember or notice if the first memory has changed or not. So the first memory could be deleted and replaced with something else, but this second part of memory can notice this. Now, if you have such a friend, and you put it in the Wigner's friend scenario, what we showed here, and people who are familiar with non-locality will see this immediately, you could signal. So you can think about this as intellectual training, saying that if you think that there is no signaling, you should not have this second part of the memory. But I want to give some seriousness to this idea by the mere fact that we can think about these experiments in somewhat operational way. Now I come to Anton's talk and his question mark, reality question mark. That's where I am closest, but I'm open. So the idea is that the facts are relative. They are relative to the context, observer, or Cavalcanti's expression, bubble. So the assumption of the existence of the joint probability was wrong from the very start. That could be an answer, and QBism, I think, will assign to that for different maybe reasons. Relational quantum mechanics, with which I have many other problems, but not this one. Or something like Neo-Copenhagen approach. And here I read the conclusion of my 2015 papers. It says, well, the view that holds the coexistence of the facts of the world, common both for Wigner and his friend, runs into the problem of hidden variable program. The solution lies in understanding the facts can only exist relative to the observer. Now, is it strange? Well, there is some analogy with the special relativity that we put forward, again, I think all three of us. Namely, in special relativity, every inertial observer claims that her or his clock ticks faster than that of a moving partner. Taken together, the claims would lead to some kind of inconsistency under inverted commas. However, the statements have only meaning with respect to the specific observer-dependent measurement procedure defining simultaneity. And that was put forward by Sudbury, if I'm not mistaken. Now, similarly, the outcomes or facts of different observers in Wigner-Friend type of experiment have only meaning relative to observer-specific experimental setup, context, in agreement with Bohr's idea of complementarity. Now, do I have a minute or two, or? Okay. People in my group know that I change my mind constantly. And I don't see this as a weakness. I'm not committed to any of, strongly committed to any of the paths. I want to challenge my understanding and deepening this, but that doesn't mean that I don't make my choices, and I don't think that I need to follow all the paths. But one thing that intrigued me is something, and what I want to look at in future is the possibility of switching between the bubbles. And in a paper with Veronica first, in the Wigner's Friends as a Rational Agent, and more recently with Flavio and Gonzalo, we took this path, and I want to read you the abstract, and you will understand from the abstract what I mean. So here we show that the situation is more symmetrical than it's usually thought. There are different types of information that each of observers has that the other fundamentally cannot have. They reside in different bubbles, in Cavalcanti's terminology. While this can explain why the objectivity of the state assignment is only relative to the bubble, we consider a more elaborated situation in a form of a game in which the players can switch between bubbles. We find that in certain circumstances, observer may be entitled to adopt and verify the state assignment from another bubble if they condition their prediction on all information that is in principle available to them. And so, it's a practical question. If some extraterrestrial civilization just tell us, guys, you're just heading to the beam splitter, how should we act? And that's what we try to answer in this paper. And finally, I think the Wigner's friend situation is not so uncommon. And and it's common to all reasonable, universal, and probabilistic theories, because these theories are probabilistic, just like quantum mechanics is. So that means that we need measurement apparatus, context, observer, to extract probabilities from a system. So there must be a division between subject and object, but it's a functional, not physical distinction. That's one part of the story. On the other hand, we want theories to be universal. Anything can be a system. Not everything, like Perez told us, but anything can be a system. So what was your measurement apparatus, Marek, maybe will not be my measurement apparatus. I will treat it as a system with respect to my measurement apparatus. So I do think you need measurement apparatus, but we don't need to agree on what they are. And I feel that any theory that is universal in that sense and probabilistic necessarily have a Wigner's-Friend situation. It's a feature, not a bug. And finally, this is my final slide, probably I'm just confused. And I like to cite here Danny Greenberg. He said, I'm confused, therefore I am. So I hope that we just overlook something, or we are not mature enough to understand the thing. With this, I would like to thank you, and also I want to thank to all of my co-authors on the topic of Wigner's friend. Thank you very much.
Thank you, Caslav, very much. We'll proceed with Eric and his presentation.
It's an honor to receive this award on behalf of all my co-authors. So first of all, let me acknowledge them: Kokwei Bong, Anibal Utreras Alarcon, Farzad Ghaffari, Yong Chang Liang, Nora Tischler, myself, Jeff Pride, and Howard Wiseman. Kokwei, Farzad, Nora, and Jeff were part of the experimental team on this paper. The other authors were part of the theory team, the two first joint co-authors, PhD students. Nora was the experimental corresponding author, and I was the theory corresponding author. And it's a special pleasure to be talking about this work on a conference celebrating the 60 years of Bell's theorem, because as I will discuss in more detail, this work opens a long-term research program which involves tests which have stronger significance than violations of Bell inequalities. The violations of LF inequalities would have stronger significance than Bell's in a way that I will discuss shortly. And I like to call this field, Nami, I'm using Shimony's term, experimental metaphysics. I learned recently that it was his term itself, he didn't coin it, was Michel Besso, Einstein's friend. But he used it to describe the field that was essentially started by Bell with his theorem, where we realized that certain hypotheses which can be seen to be metaphysical in that they don't lead to testable consequences, but also because they may be talking about things like reality and observation and our access to it, making a distinction between ontology and epistemology that generally in ordinary physics we don't. So for that reason, I think the term metaphysics is accurate. But also it's experimental because we find that certain conjunctions of metaphysical hypotheses lead to experimental consequences that can be tested. And then you can rule out whole classes of theories in doing that. Not only is it science, but it was awarded the 2022 Nobel Prize in Physics, as you all know. So to relate to Bell's theorem, I'll remind you of the first talk of this conference from Reinhold Bödelmann, where he talked about his socks and how Bell used that to explain his notion of local causality. And Bell said, the philosopher in the street who has not suffered a course in quantum mechanics is quite unimpressed by PR correlations. He can point to many examples of similar correlations in everyday life. The case of Bödelmann's socks is often cited. When you see that the first sock is pink, you can be already sure that the second sock will not be pink. Observation of the first and experience of Bödelmann gives immediate information about the second. There's no accounting for tasters, but apart from that, there is no mystery here. And it's not the API business just the same. So why is the philosopher on the street so unimpressed? They see a correlation between sock A and sock B, and they see, there's a very good explanation for this correlation. It calls for some explanation, but here's one. Betterman wakes up in the morning and he flips a mental coin in his brain, or let's just model it as an option between two different situations. If his coin, let's call it lambda, is 0, he puts the pink sock on foot A. If it's green, he puts the green sock on foot B. Otherwise, the reverse order, and let's say that that's 50-50 probability. Of course, that's a rough model of what Betterman is actually doing, but that's the kind of explanation that one has in mind. And then important thing there is knowing this fact about the common cause, the correlations factorize, and you can recover the correlation by averaging over these hidden variables. Now, you can think of this reasoning as an instance of a principle from Hans Reichenbach, a philosopher who coined it, Reichenbach's principle of common cause. That if you see a correlation between two events, you seek some kind of causal explanation. And not only that, but you seek a causal explanation which will independently explain the events so that the probabilities for those events to occur factorize. Bell's notion of local causality is almost that, just with the added assumption that any causes of an event are in its past like cone. So with those two together, you get local causality. And to get Bell's theorem, just need a couple more ingredients. First, of course, you have the choices X and Y for Alice and Bob. And you need to make an assumption that there is a single space-time out there where you can locate all of these events and talk about icons. And you assume that those events are single events. The events X, A, B, Y have been observed, and they can be located in space-time, not, say, in different branches or undefined where they are. And apart from local causality, which follows from the other two assumptions that I already mentioned, we need some assumption that plays the role of the free choice assumption in Bell. So we can use this assumption that we call local agency, that a free choice is uncorrelated with events not in its future light cone. And with that, you can derive the Bell locality condition, the factorization condition, which leads to Bell inequalities. Now, a common response to Bell's theorem, which is what you would have to do if you take the position that Bell's theorem implies a violation of realism, or implies that there are no hidden variables, or implies that outcome independence fails, but you can keep parameter independence. All those are instances of rejecting Reichenbach's principle of common cause. Now, one problem that you may think there, but then what about Betterman's socks? Why was the philosopher on the street, so quick to jump to the conclusion that that's the kind of explanation that you should be seeking? Does the world require that there must be an explanation of this kind? And how do we make sense of, say, the fact that these kinds of explanation work so well? And there's a whole book written by Julia Pearl, formulating this framework of classical causal models that's so applicable in many fields, and leaves a little bit of a puzzle of what do you do to make sense of that. Thinking about that question, in 2014 with Ray Lau, we suggested that we can break down Reichenbach's principle into two independent principles. One is the principle of common cause in self, which just says that correlations require some causal explanation. And the other is that what it means for a common cause to explain the correlations is that it factorizes the probabilities in the way that Reichenbach required. Let me also just define a notion of independent interventions, which is that an intervention is this free choice that you can make, can be made via external variables which have no relevant causes among the other variables that are relevant in your experiment. These now imply local agency, then those are sort of the errors in logical implication. And so, absoluteness of observed events, local agency, and Reichenbach's principle imply Bell inequalities, which have been shown to be violated by nature quite conclusively now. Now, what do we do with that way of resolving Bell's theorem, which rejects Reichenbach's principle? One thing you can do is the proposal that we also did in that paper, following this framework of conditional quantum states by Matt Leifer and Rob Speckens. That there's something else that factorizes, which are the Choi operators from the common cause to Alice and Bob. So they can replace this idea of decorrelating explanation in Reichenbach's principle And it's the kind of explanation that's been carried out to quite a bit of detail in this framework of quantum causal models, which I don't have time to explain here. So that's one way to to accommodate that kind of position. But one of the difficulties now is with this new no-go theorem that I'll discuss now, which uses Caslav's very great intuition about the possibility to prove a no-go theorem in this scenario, which involved two observers that we call Charlie and Debbie, and two super observers that, by assumption, can perform quantum operations on those labs called Alice and Bob. Okay, now in the way we normally present that, we say when x equals 1, Alice flips a coin. When x equals 1, she asks Charlie for his outcome. Otherwise, it may not be necessarily just two other choices, there may be three or more. She will do some other experiment. One particular experiment that she can do is reverse the unitary evolution that entangled Bob with the system. That's not the only way that she can do an experiment, and there's not a particular assumption of the theorem, just one way of visualizing what's going on. And then she proceeds to measure the system itself directly. And we can locate those events in space-time according to this diagram. Then local friendliness is the assumption of absoluteness of observed events and local agency, and then we show that from these we can derive local friendliness inequalities, which are constraints on the observable probabilities, like Bell inequalities, and which can in principle be violated by quantum mechanics if this technological assumption holds that a super observer can perform arbitrary or close to arbitrary quantum operations on an observer. And we also do a proof of principle experiment, and I'll discuss a little bit more about that soon. So just very quickly, what the no-go theorem involves, the assumption of absoluteness of observed events is, as Caslav was mentioning, the assumption that there exists adjoint probability distributions for the events that are occurring in a given run. Not all the possible outcomes of observations that may be done, but in any particular run, the ones that are observed by some observer, which are C, D, X, Y, and B, the actual values in a particular run, such that you will recover the marginals, the empirical probabilities for Alice and Bob. By this setup, there is also an assumption that when x equals 1, Alice's outcome is equal to that of Charlie, and similarly for Bob and Debbie, which is not directly following from absoluteness of observed events, but has been called an assumption of tracking by David Schmidt, Matt Leifer, and Yile Yang in a review paper. Local agency plays a similar role as the assumption of parameter independence, that's usually called parameter independence or locality in the derivation of Bell inequalities, and the assumption of freedom of choice. And from these, they imply a local friendliness model, which has a certain form, not exactly the same as just the factorizability condition of a Bell inequality, and from these we derive the local friendliness inequalities. Then these form a polytope, like the Bell polytope, which is strictly contained in the local friendliness polytope. Here the Bell polytope is in green, and local friendliness in orange, and the purple in the no-signaling polytope, and the red is the boundary of quantum correlations. And then we show that, say, there are some points here which violate a Bell inequality but do not violate any local friendliness inequalities. There are some points in which quantum correlations violate both of them. And whenever Bell inequality is violated, whenever an LF inequality is violated, a Bell inequality is violated. Any experiment that is an LF experiment is a Bell experiment. And so, meaning that the violations of LF inequalities have strictly stronger implications than violations of Bell inequalities. So let's think a little bit more about that. Some other results, these polytopes had been previously studied under the name of partially deterministic polytopes in a different context of device-independent randomness. And we recently generalized to most partite scenarios as well with my PhD student, Mawan Hadra. And also, we proved a possibilistic version of this no-go theorem, which then removes one of the possible objections, which is that about the use of classical probability in the proof. And we did a proof of principle experiment, and of course we call it proof of principle because the observer is a very simple observer, because it's the path that a photon is taking in a polarizing beam splitter. Marek would call it a pre-measurement. And asking the friend would just consist of measuring the path, and performing one or the other observations would consist in undoing that unitary evolution and performing a different measurement. Oops. We then show that we violate all of these Bell inequalities, and in particular say that some states in which that violate some Bell inequalities but no local friendliness inequalities, expressing how those are stronger conditions. Okay, now in comparing the two results, note now that those assumptions that correspond to this rejection of realism as usually thought of, and which can be made a little bit more interesting in these frameworks of quantum causal models, they cannot resolve this no-go theorem because those assumptions are not made in the derivation of the LF inequalities. And to make things worse, more recently in this paper with Vila Ying and other co-authors, we showed that even non-classical causal models beyond quantum, if you allow some arbitrary GPT causal model, you cannot explain these correlations. And also there is a version of the no fine-tuning theorem for violations of Bell inequalities that any non-classical causal model requires fine-tuning to explain correlations in an extended Wigner friend scenario. So the challenge is more complicated to maintain compatibility with these causal assumptions that were the motivation for quantum causal models, to try to maintain compatibility with these causal assumptions that are motivated by relativity and with Leibniz's principle. It seems that we need perhaps more relativity, as Caslav was suggesting. Maybe events themselves must be relative. But that's a whole research program. Of course, there's interpretations like Everett that do that, but whether that can be done, or QBism, whether that can be done in other ways, it's an interesting question, how precisely to make sense of that. Now, of course, all of this is if these inequalities are violated in a way that is convincing. And that brings us to the question, what would that look like? What would be a convincing violation of the inequalities? And then it brings to the question of what is an observer or an observation? Now, what we can prove, what any experiment can prove, is that given some criterion, some candidate criterion for what an observation is, any experiment in which has a system that satisfies that criterion, either local friendliness is false, or that criterion is not a sufficient condition for something to be an observer. So that means we learn something with these experiments that have been done, that not all physical systems can be considered observer or local friendliness is false. We don't know that local friendliness is false from the experiment, but it's some information. We learned information about a disjunction. And it is possible that the experiment could fail for more complex observers. That's for nature to decide. So where do we go from there? What's some directions that we can go? Now, one of the possibilities, of course, is to just postulate that an observation, a measurement, requires an irreversible amplification. And that's untestable. And if that's the case, the experiment cannot be done by definition. It would mean that if one day we did an experiment with a human being, we would just have to declare that that was not an observation after all. Another direction that we can consider for experiments that could potentially be done, we can divide broadly into two categories. One which look at quantitative measures of complexity or decoherence. When does decoherence happen? So you can give some sort of measure for how good decoherence has occurred, how irreversible, even though not completely irreversible, the system is. That's been done recently in a paper by Will Zhang and collaborators, looking at this branching factor in both simulations and experimental implementations in a quantum computer. Another would be some measure that would correlate with consciousness. We don't know what that is, but there's some candidate theories like IIT, integrated information theory, that if anything, what they have going for them is that there's something that you can calculate and you can test. And again, you would test a conjunction, right, of that assumption together with local friendliness. More interesting, I think, and more qualitative measures, or not measures, qualitative criteria, are situations in which we start to be, to require talking about these systems as being observers, where a sort of an intentional stance, using Bennett's terminology, starts to become useful. Well, not the first case there, there's still a qualitative criterion, which is just a system that's macroscopic, only just in the sense that it's observable by the human eye. That's something that's not too hard to imagine. The human eye can detect perhaps 100 photons. It's challenging, but not so challenging that it seems impossible. But more interesting would be systems that that require some sort of intentional stance to describe the behavior. They have agency, or there are uses of quantum theory, and then it starts opening the question of if you have to encode, program the system with some probability rules, what probability rules would you use? Would just a bond rule be enough? All the way to perhaps a community of speakers which share some sort of intersubjective agreements in reality which you can verify at least when opening the box, so to speak, all the way up to an artificial general intelligence. And for the last one in particular, we did some sort of very detailed calculations to some extent, considering an experiment in which you have to both encode this classical program as a reversible computation, consider all kinds of overheads, given the estimates for what the requirement would be for some human-level artificial intelligence. It's very challenging, extremely challenging, but not nearly as challenging as the numbers that we get if you think that what you're looking for is reversing some macroscopic object. I think that is just asking the wrong kind of question. And then finally on that, if that sounds just completely crazy to you, I would say never doubt the ingenuity of experimentalists. Hearing that from Anton Zardinger today. I think he was quoting someone else, but I think the sentiment still remains. Thank you.
Thank you, Eric, very much. We will now have Renato.
Okay. Thanks, everyone, for staying until the end of the conference. It's, of course, an honor to talk here, and I want to thank everyone who was already thanked by the other prize winners, but I also would like to actually thank the other prize winners to help making this topic of Wigner's friend more popular in the scientific community. I think it's an extremely important topic because it's a way, at least for theorists, I'm unfortunately not, I don't have this ingenuity that Anton has as an experimentalist, but as a theorist to test the limits of our currently best known theories. So I put here the title of, or almost the title of the original paper for which the prize was given with Daniela Frauchiger, and I also wanted to thank her for her contributions at that time. So she left science, but she's still following the development here. Now, there has been a lot of follow-up work, and here on the slide you see the follow-up work that has been done in my group, and also some work that is going on, in particular last one, so you see it's submitted in the future, and I will talk a little bit about that. So, if you look into the, let's say, question of Wigner's friend, as I just said, it's trying to explore the limits of quantum theory. But some people say it maybe goes a bit too far. We are now testing a theory by looking what happens if we now do some brain surgery essentially on a friend. So we have the friend in the lab, and at the end we carry out this measurement. So Caslav mentioned that this idea was introduced by David Deutsch, that we could not only have the friend in this isolated box, Wigner could later actually carry out a measurement on the friend in a superposition basis, which is probably a quite invasive thing to do. And one could say, okay, this is so artificial, maybe that's a bit problematic. But the question is, could we maybe do a Wigner's friend experiment without doing to Alice or to the friend any harm, or maybe almost no harm? Maybe you just have to push her slightly into a black hole, but otherwise she would be fine. So what I'm trying to tell you is that the experiments around Wigner's friend that we just heard about may actually be quite relevant in this larger context of testing quantum theory in connection to general relativity, and actually that thought experiments that have been proposed in the community that thinks about the compatibility between these two theories are, in a sense, also suffering problems that we see or that we have exposed in the Wigner's friend scenario. So that's somehow one of the goals here. Okay, so the question is, can we have a more natural setting in which we have something like these measurements on the friend? And you see, the setting will involve black holes, but this is a much more natural setting than having a perfectly isolated lab. Black holes at least exist. We have photographs of them, and they, in a sense, can replace possibly this thing of having measurements on perfectly isolated labs. So again, just to set the context, what is done in the, there's a big research community at the interface between quantum theory and gravity, and of course here in Vienna I don't have to tell people that Caslav is one of the leading forces in this area. And the big question is, how do these theories fit together? Do they even fit together, or are there some incompatibilities? I mean, we expect there are some incompatibilities, but the question is, what are they? What are really the conceptual issues when we try to combine the theories? Of course, there are technical issues, but I'm really more interested in the conceptual ones. So quantum theory has only been tested in a small realm. That's what is indicated here with a few spins. General relativity also has only been tested in a small realm. I mean, we have observed black holes and so on, but there's of course much more that could be tested. And in particular, we have currently no access to the intersection until maybe Markus Aspelmeier will be at the end of his big program and has done these experiments that bring these things together. Okay, so one of the thought experiments, so as I said, I'm not an experimentalist, so I return to thought experiments, and one of the, I think, really interesting thought experiments that tried to test this regime is the black hole information paradox. There are many variants of this thought experiment, but the important point is that this thought experiment involves elements from quantum theory and from general relativity. And so I would now like to talk about some work of like understanding this thought experiment in a way that links it to Wigner's friend experiment. And this is this ongoing work in the future that I'm currently trying to finish in some way. I mean, I'm talking today about it together with Ladina Hausmann, who is also here. So in case you have questions, you may help answering them. Okay, so what is this black hole information paradox? I will now already kind of change it from the standard description in such a way that suggests a similarity to Wigner's friend experiment. So we start with two agents. One is Wigner, W, and the other one is Alice. You could also think it's the friend, but because there may be other friends, as you know, in these extended Wigner's friend experiments, it's maybe good to give them more specific names. So Alice, we assume, has kind of a dilution refrigerator. That's this thing here, with some qubits inside, or some spin particles, which are entangled to some reference. So this reference here will stay outside for a long time. You can just think of this as carrying in, or Alice just starts with this entanglement, which is of course a standard thing in quantum information, that we say information carried by someone has to be about something else. So we have these entangled systems. So Alice and Wigner now continue with an experiment, which involves, as I said, Alice jumping into the black hole. So this little circle that you see should be the event horizon of the black hole, and Alice can cross it. And so you should think of this like the orders of magnitude, just to make this, in a sense, not too cruel. You can imagine this black hole is so big that the tidal forces at the event horizon are sufficiently small so that Alice doesn't feel much stress there, and she still could survive a few hours while being within the black hole if it's large enough. So I think this is, in a sense, realistic. I mean, there are black holes of that size. Now, you see this sequence of pictures. So in the first picture, Alice jumps into the black hole. In the second one, she's inside. And we know that as we cross, if a freely falling observer crosses the event horizon, probably according to our current understanding of GR, nothing special happens. So they can continue doing experiments, and in particular, Alice could now do a measurement of the spins in the, let's say, set basis, or in the computational basis, and records the outcomes. So this is what is indicated by these little sets. She has these 4 spins and gets 4 values of the outcomes. Now, meanwhile, Wigner stayed outside. And I will now assume, and this is, of course, an assumption that is not commonly agreed on, that the black hole acts a bit like a mirror, in the sense which has been described more specifically by a famous paper by Patrick Hayden and John Preskill, that if you throw some information into the black hole, as they said it will be pretty immediately radiated out again by Hawking radiation. So here what you have to, by the way, keep in mind is that Hawking radiation is really an effect, or one of the few effects that is well understood, despite the fact that we don't have a theory of quantum gravity, because it's in a regime that is kind of accessible, but it's really a quantum gravity effect. It's an effect in the sense that it's involving gravity, and quantum field theory on curved space-time. And if you now want to argue that there is also information carried by the Hawking radiation, you need to assume that the black hole actually emits really energy to the outside and gets smaller, and that this energy could carry information. And so many in the community see this as a good model to assume that what will happen is that the radiation, so if you look at the whole process from the outside, from Wigner's viewpoint, it will look as if there was just a huge unitary going on. So there is Alice falling in, and then the radiation will just be some unitary evolution of the state of what fell in. So in this case of Alice together with her system. So this means that if Wigner now places an array of detectors around the black hole, he could just capture this radiation. So the radiation, by the way, will be mostly actually photons, you could imagine, depending on how we prepare the black holes. So this is something he could capture. And then he could, because everything is unitary, has in principle all the information of what fell in, he can now perform a measurement. And if Wigner performed a measurement in his computational basis, this would be a very complicated measurement in terms of, in a sense, the original basis of how Alice fell in, because there was this scrambling unitary of that made out of Alice the black hole radiation from Wigner's viewpoint. So anyway, we will assume that Wigner can collect this radiation and then carry out a measurement that will give him the same information as if Alice had carried out a measurement in the X basis. So that's a different basis than Alice used. So he just he captures everything, and so in particular he also gets, of course, the spins that fell in, and can now perform a measurement on them. So Wigner now has information in the X basis about the spins. Now there's an important point in this consideration. You notice there are 2 agents that were involved, and you could ask, why did I even include 2 agents? We could just have a notebook falling in and no agent Alice, and maybe still say stuff like we can get the information from the notebook. But one important thing is that in general relativity, if we want to do the analysis, we have to first also choose an observer or a reference frame. And for example, if we take as a reference frame an outside observer like Wigner in this picture, this reference frame will just not cover the inside of the black hole. So in other words, in Wigner's description of what's going on, there is no inside. That's the whole point of an event horizon. There's just nothing behind that horizon from Wigner's viewpoint. But the event horizon is a subjective notion. It depends on the fact that Wigner stays outside. It's different for Alice who falls in. For a falling observer, there is another reference frame, another coordinate system, if you think in GR terms. And this coordinate system will cover the inside of the black hole as well. So we do actually do 2 different analyses of the situation. One from Alice's viewpoint, which includes the inside. Ultimately, she will be there. And from Wigner's viewpoint, who will always stay outside. And in a sense, this is already comparable to when we talk about the Heisenberg cut in quantum theory. So what I mean here by the Heisenberg cut is we choose an agent has to choose what system he wants to describe. In this particular case, Wigner decides to stay outside and only describe the outside of the event horizon, whereas Alice decides to jump in, and with that has a different Heisenberg cut. She describes a system that includes the inside. But there are different regions that are captured. So the Heisenberg cut is kind of the cut around the system which we want to describe using our formalism, or our theory, in this case quantum theory, together with GR. So the next slide is the same slide, but it makes this more explicit, because this is really an important point. So the numbers now have colors, and the green color stands for, this is just Alice's viewpoint. So from Alice's viewpoint, there is an inside. She can talk about the device she has, the dilution refrigerator with the spins inside, and she can talk about the measurement outcomes which are stored somewhere. So the first two pictures are from Alice's viewpoint. The second two pictures, 3 and 4, are from Wigner's viewpoint. And you see from Wigner's viewpoint, there is no Alice at the point once she fell inside. Of course, at the beginning, as long as she's outside, she still exists in Wigner's view, but afterwards, there's just Hawking radiation, but there is no Alice any longer. And nonetheless, he can, of course, now talk about this Hawking radiation and that he retrieves whatever would have been these spin qubits. So we have these two different so-called Heisenberg cuts in this gravity experiment. And this is, of course, very similar to how we think of Wigner's friend experiments. So we have the Heisenberg cut of the friend, which is, in this case, just, here this is now a different scenario. The friend is just in the usual Wigner's friend experiment in an isolated box and talks about the qubits or the spins, the 4 spins in the dilution fridge. And so his Heisenberg cut would be around that fridge, so it's somewhere like this. Conversely, Wigner's Heisenberg cut is such that it includes the whole isolated lab. That's how we think usually in the Wigner's friend scenario. So in that sense, there is an analogy in this conceptual sense. Now, at this point, both paradoxes, the Wigner's friend paradox and this black hole information paradox that I just described, are not really paradoxes in the sense that there is a contradiction. In the Wigner's friend paradox, this is just a standard Wigner's friend experiment. We could say Wigner never can talk to the friend, or if he does, then of course it destroys the superposition. So there's not really a contradiction. We have just 2 viewpoints, but they are never compared. Conversely, similarly, in the black hole information paradox, we just have Alice, who is now inside of the black hole, and Wigner, who is outside, and they just describe different areas of the universe, if you like, so they can also not compare their views, and therefore there is not really a contradiction. And that's what people called the black hole complementarity. They're just 2 complementary views, and we shouldn't compare them, and that somehow resolves the issue in the sense that there's not really an operational contradiction. But that's, of course, not the end of the story. In particular, as you just heard from the other talks, we have this extended Wigner's friend experiment that turned this original scenario proposed by Wigner into something which is, I would say, in an operational sense, much more or leads to a contradiction, of course, still under certain assumptions, which I will come to. So the extended Wigner's friend experiment look like this. You have just seen them before. Usually you have now not only 1 friend, but 2 friends in 2 isolated labs. In the version that I have developed together with Daniela Frauchiger, the 2 friends labs actually at some point exchange 1 qubit of information. This could also be done differently. There are equivalent descriptions. And there is also communication between the outside Wigners. And so at the end, one analyzes what the different agents, how they kind of think about the situation. But now that the scenario is arranged in such a way that they can really come to potential contradictions. So let me again return to the black hole information paradox and tell you what that would mean in that particular case. And that's even what is done. So that's not kind of a completely new thing. So what happens in the black hole information paradox? In the black hole information paradox, so far, we are at point 4, or at picture 4. Now, the next step would be that there is an additional agent we introduce, like in the extended Wigner's friend paradox. The blue one, let's call her Ursula. That will be a similar position as in the extended Wigner's friend paradoxes. She talks to Wigner, and then also, of course, then knows what Wigner's measurement outcomes are. And then she also jumps into the black hole in picture 6 and compares and just asks, she will meet Alice there. So the black hole really has to be big enough so that Alice can still be reached once Ursula jumps in and asks Alice what outcome she got. Now, Ursula is like a referee. She has now the two views. She could collect the two views, the view of Wigner and of Alice, and in that sense could potentially compare them. And now you already see this is a seemingly contradictory situation, because now we are in a, or let me explain again, by the way, before I come to the contradiction, that again one has to be careful about the viewpoint. So I now put blue numbers on the new two pictures, indicating that this is now the viewpoint of this third agent that I introduced. And this third agent is again a free-falling one. So this agent has a coordinate system that includes seeing Wigner and seeing Alice. But for example, this Ursula would never see the Hawking radiation. For a freely falling observer, there is no, or basically no Hawking radiation. You can at least arrange it in such a way that there is none for them. So Hawking radiation itself, the existence of the radiation, is an observer-dependent effect. So we cannot just say Wigner now jumps in, because for Wigner the Hawking radiation existed. So we have this third party which is free-falling, and being free-falling means that you have a completely different view of is there radiation or not. So what one would appear as a fact, there is radiation or not, is just an observer-dependent thing in this scenario. So now, why is this a contradiction? So Ursula now has collected the information from Wigner and from Alice, and one was the measurement in the X basis, one in the Z basis. And we know from quantum theory this shouldn't be possible. We cannot know both the outcome of a measurement in the X basis and the Z basis, because usually we have to decide to do one of the two, but we cannot do both. And actually, we could even lead that to an operational contradiction. We could say there was this reference outside that was always there. So you see it here. Oops. This one. And so we could have even a fourth agent who is now testing. So even later, the agent jumps in and says, please, Ursula, tell me what these outcomes are for the measurement, for the X and Z measurement, and then this new agent, the pink agent, could measure the spins and check whether the outcomes, the claims are indeed correct, because initially, you remember Alice's spins were perfectly entangled, or were assumed to be entangled with the reference, so this means they should get the same outcome. So if the pink agent now measures a spin where Alice said, or where Ursula said the X value is pointing in that direction, she should be able to confirm that. And that should not be possible. That would be kind of a certification that something like cloning happened, because we know we cannot predict both values at the same time. So we really arrive at the contradiction in this information paradox. And now I come to the central question, kind of, which I want to answer in a sense. What's actually the origin of this contradiction? So at the beginning I said the whole motivation for the black hole information paradox was to test the consistency of quantum theory and gravity. But the Wigner's friend experiments, which are very analogous to what I just said, they just test the consistency in the sense of quantum theory itself. So now one could wonder, as there is such a kind of striking analogy between the two scenarios, could it be that the contradiction arises not because of the combination of relativity and quantum theory, but just because quantum theory itself is already, in a sense, has its boundaries or limits, or has certain conceptual problems that we cannot resolve. So let's therefore go back again to two of the pictures I showed you before, two stages of the black hole information paradox. And these are important stages which are seemingly harmless. Namely, there was a stage when the new agent that I introduced, whom I called Ursula, was talking to Wigner and asking, what were your measurement outcomes? And Wigner would just tell him, these were my outcomes, these were the X values. And later, again, the same agent, Ursula, talked to Alice once in the black hole and asked Alice, what are the outcomes you got? And will also accept that these are the correct outcomes, I mean, that Alice tells him the truth. So he kind of accepts that it's correct what he's told. He's told something about the outcomes, about events in the language that we heard before, and just accepts that these events are also events with respect to him. And now, after the two previous talks, of course we know this is problematic. My way to say why it's problematic, and this is different in the different formulations of our Wigner friend experiments, is that it has to do with a kind of new test you can do for a theory. You can always test whether a theory is self-consistent in the sense that the theory is able to describe an agent who uses the same theory. So what I mean by that is, if you have an agent, the green one here, now you don't have to think of the information paradox, just take an agent like the green one who uses quantum theory to reason about an object. This could be a quantum object, a quantum book. Now, this agent uses quantum theory to reason about it and has therefore a mental picture or a formal, like quantum mechanical picture of what this is. Now imagine another agent, a blue one, who now reasons up. So this agent uses quantum theory, that's the important thing, to reason about how this agent uses quantum theory. That's referring to the original title of our paper. Quantum theory cannot consistently describe the use of itself. So here it's really, this person uses quantum theory to describe someone who uses quantum theory, and we want to remain consistent. So that's one assumption. The other assumption is now this one, and this is what we call the consistency requirement. The consistency requirement is that if the blue agent here comes to the conclusion that the green agent came to a particular conclusion here in this little bubble, then if all agents are trustworthy in the sense they're just using the same theory, they agreed what is quantum theory and are all using that, then the blue agent can conclude that whatever the green agent concluded should also be true for him or her. So it's kind of a transitivity of knowledge. And this transitivity of knowledge was used in the black hole information paradox, because whenever agents talk to each other and take it for granted that whatever they are told is correct, they use that in a sense. So now the problem is that what was shown in our paper is that these two assumptions that we can reason using quantum theory with an arbitrary Heisenberg cut, so this means in particular we can reason about other agents who are using quantum theory, that's this assumption Q, together with this consistency assumption that I just mentioned or briefly explained, which one could say is a kind of transitivity of knowledge, or allows us to transfer knowledge. In a sense, as you're listening to my talk, if you are not just hearing that as words, but try to make sense of it, you're probably somehow using that assumption. These two things are incompatible in these extended Wigner friends experiments. So in other words, they are already problematic in quantum theory itself. And so this actually answers, in a sense, this question. We know that the assumptions that were used here in the black hole information paradox, if I take the same assumption, namely that information can be transferred from people who use different Heisenberg cuts to each other, this is clearly the case in this black hole information paradox, that this assumption, if you use it in a bare quantum context without any GR, already leads to contradictions. So that was what the theorem said. So in other words, we know the assumptions that enter actually here are already problematic here. So in other words, we cannot conclude from the black hole information paradox that there's a problem in the connection between quantum theory and general relativity. The problem may already lie in quantum theory itself. Of course, together with this transfer of knowledge assumption, but we first has to replace it with something else, because if you don't replace it with something else, we can anyway not carry out this experiment here, so we need it. So that brings me to the conclusion. So the conclusion is, I've showed at the beginning a slide where I had a question mark here at the inside, asking, are the two theories compatible? Now, what the Wigner's friend experiment tells us is that the same assumptions that enter the black hole information paradox already lead to problems here. So maybe the black hole information paradox, the paradox or the contradiction that arises there is actually a pure quantum paradox. That's it. Thanks.